let's take a deep breath, relax, and slowly explore the story of astronomy. Somewhere in what is now southern France, roughly 17,000 years ago, a person stood inside a cave and painted. The walls of Lascaux were already alive with images of bulls, horses, and deer, drawn in earthy reds and blacks with a skill that still takes your breath away. But above one great wild ox, the painter added something that was not an animal at all. It was a cluster of 6 small dots, carefully placed above the creature's shoulder. For a long time, those dots were thought to be simple decoration, nothing more. But in the late 1990s, a German researcher looked again and noticed something quietly remarkable. The dots matched the positions of the Pleiades, that little group of stars you can still see with your own eyes on a clear winter night. The bullseye lined up with a bright star we call Aldebaran. And if this was right, then a cave painter had created a star map on a stone wall 15,000 years before anyone would think to build a telescope. Can you picture that for a moment? A person standing in flickering torchlight deep inside a cave, painting the stars they had memorized from nights spent watching the open sky. We do not know their name. We do not know if they were young or old, man or woman, but we know they looked up and they remembered what they saw. And that impulse, that desire to watch the sky and make sense of it, is as old as we are. Before there was electric light, before there were cities or roads or farms, the sky after sunset was the most dramatic thing a human being could witness. The Milky Way stretched overhead like a glowing river, bright enough to cast faint shadows on the ground. The moon changed its shape from a thin sliver to a full glowing disk and back again, roughly every 29.5 days. Planets drifted among the stars in slow, wandering paths. And along the coasts, the tides rose and fell in a rhythm that echoed the phases of the moon. The sky was not just beautiful, it was useful, and paying attention to it could mean the difference between eating and going hungry, between knowing the seasons and being caught off guard. Some of the oldest objects ever found by archaeologists may contain the earliest attempts to track the moon. In the mountains between South Africa and a small country called Eswatini, a piece of baboon bone about 42,000 years old was discovered with 29 small notches carved into its surface. Some researchers believe those notches are a count of the moon's phases, one mark for each night of the lunar cycle. A similar bone, found near a river in Central Africa and roughly 20,000 years old, carries 3 columns of grouped notches that may represent a 6-month lunar calendar. Not everyone agrees about what these bones mean, and a single carved bone is not proof of anything on its own. But taken together, they suggest that people were counting the moon's changes tens of thousands of years before the invention of farming, or writing, or anything else we usually associate with civilization. And then, at some point, people began to build. Not just small markers or scratches on bone, but great structures aligned with the sky. In the desert of southern Egypt, about 700 miles south of the Great Pyramid, a circle of small standing stones called Nabta Playa was built more than 7,000 years ago by cattle herders who gathered near a seasonal lake during the summer rains. Some of the stones point toward the sunrise on the longest day of the year, and longer rows of stones may have aimed at the rising positions of bright stars. Nabta Playa is older than Stonehenge by at least 2,000 years, and its builders left no written explanation of what they were doing. The stones speak only through their positions, and we can only guess at their meaning. Far to the north, in what is now Germany, the Gösek Circle was built around 4,900 years before our era. It was a ring of ditches and wooden fences, about 75 meters across, with openings that lined up with the sunrise and sunset on the shortest day of the year. The people who built it were farmers, living in small communities, and they understood the path of the sun well enough to carve it into the earth. And then there is Stonehenge, perhaps the most famous ancient monument in the world, its great stone arches standing on a plain in southern England. The site grew and changed over more than 1,000 years, from a simple ditch around 3,000 years before our era to the towering stone circle we recognize today. On the morning of the longest day of the year, the sun rises just beside a distant stone and sends its first light straight into the heart of the monument. On the shortest day, the setting sun does the same from the opposite direction. People came from miles around, bringing animals for feasting, and the remains of their celebrations have been found in the earth nearby. What did all of this mean to the people who built it? We cannot be sure, but we can see that across enormous distances, separated by thousands of years, human communities decided on their own that the movements of the sun, the moon, and the stars were important enough to preserve in stone. The effort was enormous. Some of the stones at Stonehenge weigh as much as 25 tons and were dragged from hills more than 20 miles away. This was not something people did on a whim. The sky mattered to them deeply in ways that shaped how they spent their time, their strength, and their lives together. On the other side of the world, a different kind of sky knowledge was being passed down, not in stone, but in stories and songs. The Aboriginal peoples of Australia, whose cultures reach back over 65,000 years, developed some of the oldest ways of understanding the sky that we know of. And here is something lovely and unusual about their tradition. While most sky-watching cultures focus on the bright points of the stars, Aboriginal Australians also paid careful attention to the dark spaces between the stars. The most well-known example is the emu in the sky, a great shape formed not by stars at all, but by the dark clouds of dust visible against the glowing band of the Milky Way. The emu's head sits near the Southern Cross, and its body stretches along the sky toward the constellation of Scorpius. When the emu shape appears to be running across the sky, it is time to hunt emus on the land below. When it appears to be sitting, it is time to gather their eggs. This is astronomy woven into the rhythms of daily life, as practical as a calendar and as beautiful as a painting. What connects all of these early sky watchers, from the cave painters of France to the stone builders of Egypt and England to the storytellers of Australia, is a single, deeply human recognition. We are not just creatures of the earth, we are watchers of the sky. Those ancient people could not explain what they were seeing in the way we do today. They did not know that the stars were burning furnaces unimaginably far away, or that the dark shape of the emu was made of interstellar dust. But they looked, they noticed, and they found ways to remember what they learned and pass it on. And in doing so, they laid the very first stones of the science that would one day send telescopes into orbit around the Earth. And so our story begins with that first long look upward. Let us follow it now, across centuries and continents, and see where it leads. On a spring evening in the 7th century before our era, a scribe in the ancient city of Nineveh sat before a damp clay tablet, pressing the wedge-shaped tip of a reed into its surface. He was not writing something new. He was copying a text that had already been old for centuries, a guide to the stars known by its opening words as the Plough. The tablet listed 66 stars and groups of stars, gave the dates when they rose and set, and laid out what may have been the first true star map in human history. The scribe could not have known that his work would survive buried in rubble for over 2,500 years, only to be dug up by archaeologists in the 1800s, with its markings still perfectly readable. And this copied tablet was not the beginning of the story. It was closer to the end. The roots of sky watching in that part of the world, the land between the Tigris and Euphrates rivers, stretch back to the very earliest days of civilization itself. The Sumerians, who built the first great cities thousands of years before that scribe in Nineveh, were already naming the planets and tracking their wandering paths across the sky. They called the bright planet we know as Venus by the name of their goddess of love and war, and they recognized that the brilliant star you could see in the morning and the one you could see in the evening were actually the same object. That seems obvious to us now, but it was a genuine discovery. one that the Greeks would not make for themselves until centuries later. The Sumerians also gave us the number system based on 60 that we still use every day. 60 seconds in a minute, 60 minutes in an hour, 360 degrees in a circle. All of that comes from people who lived in mud brick cities along the Euphrates more than 4,000 years ago. When the Babylonians rose to power around 1800 years before our era, they inherited all of this knowledge and added something that changed everything. They began to keep records, careful and continuous records, stretching over hundreds of years. One of the oldest surviving records of a planet's movements is a tablet from roughly 1650 before our era that tracks the appearances and disappearances of Venus over a period of about 21 years. These observations were not made out of simple curiosity. In that culture, the movements of the stars and planets were messages from the gods, and reading them correctly was a matter of life and death, especially for the king. The most important collection of these heavenly messages filled roughly 70 clay tablets and contained over 7,000 individual predictions, linking what happened in the sky to what might happen on Earth. When a lunar eclipse occurred, for example, it was seen as an attack on the king, a sign that the gods were angry. The practical response to this belief was rather extraordinary. When an eclipse was predicted, a substitute would be placed on the throne, often a prisoner or a criminal, dressed in the royal robes and given the royal food. The real king would go into hiding under a false name while the substitute sat in state and absorbed whatever divine punishment the eclipse was meant to deliver. Once the eclipse had passed without harm, the substitute would be quietly removed, sometimes fatally, and the rightful king would return. Letters from court advisors describe this ritual in calm, matter-of-fact language, as though it were simply part of how things were done. The entire system depended on being able to predict eclipses in advance, which gave the astronomers of Babylon enormous power and a very strong reason to get better at their work. And they did get better. By comparing their centuries of careful records, they discovered a pattern that we now call the Saros cycle, a period of roughly 18 years and 11 days, after which eclipses repeat in nearly the same order. They did not understand the geometry behind this pattern, the way the Earth, Moon, and Sun line up to create eclipses. But they recognized the rhythm with enough accuracy to issue warnings months or even years ahead of time. This was practical science of the highest kind, driven not by curiosity about how the universe works, but by the urgent need to keep the king alive. Beyond eclipses, Babylonian astronomers developed remarkably advanced ways of calculating where the planets would be in the future. By the last few centuries before our era, they were using mathematical methods so precise that they would not be matched in Europe for over 1,000 years. They could calculate the movements of the moon and the planets using patterns of numbers that rose and fell in regular sequences, a bit like the teeth of a saw. This approach was fundamentally different from what the Greeks would later do with circles and geometry, and in some ways it was more practical and more accurate for the specific job of making astronomical tables. One of the most lasting gifts these astronomers gave to the world was the zodiac. By about 500 years before our era, they had divided the path of the sun across the sky into 12 equal sections, naming each one after a group of stars. The names they chose, the ram, the bull, the twins, the crab, the lion, and on through the fish, are still with us today, passed from Babylon to the Greeks and from the Greeks to the modern world. The zodiac was originally a practical tool for pinpointing where a planet was in the sky, not a framework for fortune-telling, though it would eventually become that too. The oldest known personal horoscope, linking the position of the planets at the moment of someone's birth to their future fortune, dates to about 410 years before our era, making it a late Babylonian invention. The influence of Babylonian astronomy spread far beyond the rivers of its homeland. In the 4th century before our era, Greek scholars traveled east and studied Babylonian data. A Babylonian priest established a school on a Greek island and taught the knowledge of the stars to a new audience. Through these encounters, Babylonian observations entered the Greek world, and from there they flowed into the traditions of the Islamic world and eventually into European science. The 60-based number system, the zodiac, the habit of keeping patient records over long stretches of time. These were all Babylonian contributions that shaped the course of astronomy for thousands of years to come. Yet the Babylonians themselves never wrote a grand theory about why the sky behaves the way it does. Their brilliance was in watching, recording, and calculating, not in asking the deeper question of what makes the planets move. That question, the question of the hidden machinery behind the sky, would be taken up by thinkers far to the west on the shores of the Mediterranean. But when those Greek philosophers began their work, they had Babylonian data in their hands, Babylonian patterns in their minds, and Babylonian numbers on their tablets. And so, as the last Babylonian astronomers worked quietly in temples that were already crumbling around them, their knowledge was already traveling outward, copied and translated, absorbed into new languages and new systems of thought. The stars they named still carry faint echoes of their names, and every time we divide a circle into 360 degrees, we are counting in the way they taught us. Let us travel now to another ancient river, and another civilization that watched the sky with equal devotion, but for reasons all its own. In the darkness before dawn on a July morning, roughly 4,500 years ago, a priest stood on the roof of a temple near the great city of Memphis and watched the eastern horizon. The air was still warm from the day before, and the river Nile lay low and sluggish in its banks, the fields around it baked dry after months without rain. The priest was waiting for a single star. When Sirius, the brightest star in the night sky, appeared above the horizon for the first time after weeks of being hidden in the sun's glare, rising just minutes before sunrise erased it from view, the priest would know that the most important event in the Egyptian year was about to begin. Within days, the Nile would start to rise, fed by rains falling 1,000 miles to the south in the mountains of what we now call Ethiopia. The flooding of the Nile was life itself for Egypt, and the rising of Sirius was its herald. To the Egyptians, Sirius was far more than a useful marker in the sky. It was the heavenly form of the goddess Isis, who wept for her dead husband, and whose tears, so the old stories said, caused the river to flood each year. The sky and the sacred stories were woven together so tightly that you could not separate one from the other. Watching the stars was an act of devotion as much as it was a practical skill, and this single observation, repeated every year for 3,000 years, became the anchor of the entire Egyptian calendar. The calendar the Egyptians built around Sirius was elegant in its simplicity. They divided the year into 3 seasons of 4 months each. The first season was the time of flooding, when the river spread across the fields and left behind a layer of rich, dark soil. The second was the time of growing, when the crops pushed up from that soil. And the third was the time of harvest, when the grain was gathered and stored. Each month had 30 days, and 5 extra days were added at the end of the year for festivals honoring the gods. That gave a total of 365 days, remarkably close to the true length of a year. But because they did not add a leap day, the calendar slowly drifted, falling behind by 1 day every 4 years. Over centuries, this small drift added up until the calendar and the stars no longer agreed. It took roughly 1,461 years for the cycle to come full circle and the calendar to realign with the rising of Sirius. This long cycle became an important tool for modern historians trying to pin down the dates of ancient Egyptian events, though the calculations depend on assumptions about exactly where the observations were made. The Egyptians found another use for the stars that shaped something we all carry with us today, the 24-hour day. They divided the night sky into 36 groups of stars, each linked to a 10-day period. As the Earth turned, these groups rose one after another above the eastern horizon, and by watching which group was rising at any given time, the Egyptians could tell what hour of the night it was. These star clocks have been found painted on the insides of wooden coffin lids, dating back more than 4,000 years. The dead, it was believed, needed to know the time even in the afterlife, so they could navigate the underworld and follow the sun god on his nightly journey through darkness. From these divisions came the practice of splitting the night into 12 hours, and eventually the day into 12 hours as well, giving us our familiar 24. It is a quietly remarkable thing. Every time you glance at a clock and see its face divided into 12, you are using a system that began in the burial practices of ancient Egypt. But perhaps the most famous connection between Egyptian civilization and the stars stands on the plateau of Giza. The Great Pyramid, built around 2,560 years before our era as the tomb of Pharaoh Khufu, has its four sides aligned to the four directions of the compass, north, south, east, and west, with an accuracy that is breathtaking even today. The difference from true north is less than 1/12 of a degree, a tiny fraction that would be difficult to achieve without modern instruments. How did the builders manage it? One widely respected idea suggests that they used two stars that happened to orbit close to the north pole of the sky at that time, watching for the moment when both stars lined up vertically, and using that line to find true north. The star closest to the North Pole in those days was not the one we call the North Star today. Because of a slow wobble in the Earth's spinning, different stars take turns pointing north over a cycle of about 26,000 years. The North Star of the pyramid builders was a faint star in a constellation we call the Dragon, and the pyramid's inner shafts may have been aimed at the spot in the sky where that star reached its highest point. Inside the pyramid, narrow passages lead upward from the burial chambers at carefully chosen angles. One points toward the region of the sky where the North Star of that era would have appeared, and another points toward the belt of the great constellation of Orion, which the Egyptians linked to Osiris, the god of the dead and ruler of the underworld. These shafts may have been symbolic pathways for the soul of the pharaoh, guiding it upward to join the stars that never set below the horizon, the stars the Egyptians called the imperishable ones. The tomb of a powerful official named Senenmut, who served the famous Queen Hatshepsut around 1470 years before our era, contains one of the most beautiful astronomical ceilings in all of ancient Egypt. Painted on the stone above his burial chamber is a map of the sky, showing the star groups used for telling time at night, the planets known to the Egyptians, and the shapes of the northern constellations, including a bull's leg that corresponds to what we call the Great Bear. It is the earliest known attempt to paint a complete picture of the visible sky on a single surface, and it tells us that Egyptian sky knowledge went far beyond counting floods and telling time. These were people who cared about the sky for its own sake and who wanted to take their understanding of it with them into eternity. In the centuries that followed, something remarkable happened. When Alexander the Great conquered Egypt and Greek rulers took the throne, two great traditions of sky watching began to flow together. The Library of Alexandria became the center of astronomical thought for the ancient world, and in that rich, mixed environment, Egyptian patience with careful record-keeping merged with the Greek love of geometric theory. The result was a burst of discovery more powerful than either tradition could have produced alone. We will hear more about that in sections to come. For now, let us linger one moment longer on the banks of the Nile. The star Sirius has not changed. On certain summer mornings, it still appears on the eastern horizon just before dawn, exactly as it did for those priests 5,000 years ago. The great dam at Aswan has tamed the river, and the floods no longer come. But the star still rises, patient and bright, indifferent to the changes below. And somewhere in the desert, the pyramids still point toward a spot in the sky where a North Star used to be. Let us travel east now to a land where astronomers served the emperor and where the sky was the voice of heaven itself. In the summer of 1302 years before our era, the court of the Shang dynasty was thrown into alarm. The sun, which had been burning steadily in the midday sky, began to disappear. A dark shadow crept across its face, and within minutes, daylight faded to a strange and sickly twilight. The court diviners, whose sacred duty it was to interpret the will of the gods and the ancestors, reached for tortoiseshell and ox bone. They heated the bones until they cracked, and then inscribed their questions and the answers they believed the heavens had given, in the sharp angular script we now call oracle bone writing. The record they left of that solar eclipse would survive for more than 3,000 years. And in the 20th century, scientists would use that very inscription to help measure how much the Earth's spinning has been slowing over the ages. A moment of panic in an ancient palace recorded on a piece of bone became a data point for modern science. The explanation people gave for eclipses in China was vivid and dramatic. A great celestial dragon, or sometimes an enormous dog, was said to be devouring the sun. The response was equally dramatic. Drums were beaten, arrows were shot into the sky, and a great noise was raised to frighten the creature away. The strategy always worked, of course, since the sun always returned, which no doubt made the ritual seem very effective indeed. But behind the mythology, a quieter and far more patient tradition was at work. The court astronomers of China were expected to predict eclipses before they happened, and the penalty for failure could be severe. An old story tells of two astronomers who were executed for failing to predict a solar eclipse, a tale that may be more legend than history, but which captures perfectly the pressure these skywatchers worked under. What sets Chinese astronomy apart from nearly every other tradition in the ancient world is the length and continuity of its records. From the oracle bones of the Shang dynasty all the way through to the 17th century, when European missionaries introduced new methods, Chinese astronomers kept a nearly unbroken chain of observations stretching over 2,000 years. By about 750 years before our era, their records of solar and lunar eclipses had become detailed and systematic. A historical text covering the period from roughly 700 to 480 years before our era records 37 solar eclipses, of which 33 have been confirmed by modern calculations. No other civilization anywhere in the world produced a comparable record over such a stretch of time. The reason for this extraordinary continuity lies in the way Chinese society was organized. In China, astronomy was not a hobby or a private pursuit. It was a function of the government itself. The Astronomical Bureau was a government office, staffed by professional astronomers whose main duty was to maintain the calendar and to report celestial events to the emperor. And the calendar was not simply a useful tool for scheduling. It was a symbol of the emperor's divine right to rule, his harmony with heaven. A correct calendar proved that the ruler was in step with the cosmos. An incorrect one suggested that the heavens had withdrawn their approval. Producing a new and better calendar was one of the first things a new dynasty would do after seizing power, as a statement of both practical competence and heavenly favor. The earliest Chinese star catalogues appeared during the Warring States period, around the 4th century before our era, when two astronomers compiled lists that together included over 800 stars arranged into about 120 groups. One of these astronomers is sometimes credited with having spotted one of Jupiter's moons with the naked eye, nearly 2,000 years before the telescope was invented. The claim is based on a passage in an old text describing a small companion star near Jupiter, and it remains a matter of debate. What is certain is that these early catalogues organized the sky in a way quite different from the Babylonian approach. Instead of dividing the path of the sun into 12 sections, as the Babylonians did with their zodiac, the Chinese divided the sky near the celestial equator into 28 unequal segments, each marked by a particular group of stars. The Chinese sky was centered on the pole, the still point around which everything turned, while the western sky was centered on the path of the sun. It was a fundamentally different way of looking at the same heavens. One of the most remarkable events in the entire history of Chinese skywatching took place in the year 1054 of our era. Astronomers of the Song dynasty recorded the sudden appearance of a brilliant new star in a part of the sky near what we call the constellation of Taurus. The star was so bright that it could be seen in broad daylight for 23 days in a row, and it remained visible at night for nearly 2 years. The court astronomer who filed the official report noted that the star was yellowish in color, and he recorded its exact position with care. Japanese astronomers also noticed the new star, as did observers in the Middle East, but no European record of the event has ever been found, which tells us something about the state of sky watching in 11th century Europe. Centuries later, modern astronomers pointed their telescopes at the same spot in the sky and found a beautiful, expanding cloud of gas, the remains of a star that had exploded in a spectacular death. We call it the Crab Nebula, and at its center spins a tiny, incredibly dense star, the collapsed core of the original, rotating many times each second. The careful record kept by a Song dynasty astronomer nearly 1,000 years ago remains one of the most important pieces of evidence we have about this object. Chinese astronomical instruments reached a remarkable level of skill during the medieval period. In 1088, a brilliant inventor named Su Song completed an enormous clock tower in the Song dynasty capital. Standing about 40 feet tall, the tower held a water-powered model of the heavens on its roof, a globe of the sky inside, and a mechanical clock with rotating figures that announced the hours. The entire machine was driven by a water wheel with a device that controlled its movement in careful steps, a technology that appeared in China roughly 2 centuries before similar mechanisms emerged in Europe. Su Song wrote a detailed book about his creation, with diagrams so precise that modern engineers have been able to build working copies. The clock tower was destroyed when enemy forces captured the capital in 1127, but the book survived. 2 centuries after Su Song, an astronomer named Guo Shoujing, working under the patronage of the great Mongol Emperor Kublai Khan, pushed Chinese observational astronomy to its highest point. He designed new instruments that were simpler and more accurate than any that had come before, built a massive stone structure 40 feet tall for measuring the sun's shadow with extreme precision, and established a network of 27 observation stations spread across the vast Mongol Empire. His calendar, adopted in 1280, calculated the length of the year as 365.2425 days, a figure that matches the value used by the calendar most of the world follows today, and he arrived at this number 300 years earlier without a telescope, relying only on the size and care of his instruments. The story of Chinese astronomy is not a story of grand theories about why the heavens move as they do. It is a story of patience, precision, and an unbroken tradition of watching. The records left behind by those court astronomers, the eclipse logs, the comet sightings, the notes on guest stars and planetary positions remain useful to scientists today, thousands of years after they were written. And so, as we leave the courts of China and turn our gaze westward across the Pacific, let us carry with us an appreciation for those quiet watchers who spent their lives recording what they saw in the sky, never imagining how far their notes would travel. On a clear evening in the 9th century of our era, an astronomer stood atop a circular stone tower at the great city of Chichen Itza, on the flat limestone coast of what is now Mexico, and watched Venus sink toward the western horizon. The tower had a spiral staircase winding through its interior, and the Spanish would later call it the snail for that reason. But its purpose was not decorative. Its grand staircase faced a direction that made no sense for ordinary architecture, but was almost perfectly aligned with the farthest point Venus reaches in the sky during its cycle. From narrow windows near the top, the astronomer could track the planet's appearances and disappearances with a care and precision that matched anything being done anywhere else in the world at that time. The observations gathered from towers like this one were recorded in folding books made of bark paper, painted in black and red ink. One of these books, which we now call the Dresden Codex, has survived the centuries, and within its pages lies something quietly remarkable. The Maya astronomers who filled those pages had calculated the time it takes Venus to complete one full cycle of evening appearances at 584 days. The actual figure measured with modern instruments is 583.92 days. The difference amounts to less than 2 hours over the entire cycle. These were people working without telescopes, without clocks, without any of the tools we might consider essential, and they achieved an accuracy that still commands respect. Venus held a powerful and fearsome place in Maya belief. The planet was linked to warfare, and its first appearance as a morning star after a period of being hidden from view was considered the right moment to launch an attack. Scenes carved in stone and painted on pottery show warriors dressed as Venus gods, leading raids timed to the planet's rising. The Venus tables in the Dresden Codex track the planet's movements over a period of 104 years, and they include careful corrections to account for the small difference between the ideal cycle and the real one. These corrections work like a kind of leap day system for Venus, keeping the predictions accurate over very long stretches of time. A study published in the early 21st century suggested that a specific individual, a single astronomer working at Chichen Itza during a particular window in the 9th century, was responsible for the clever mathematics behind these corrections. This was not faceless tradition. It was the work of a mind, a person we will never know by name, solving a real problem with real skill. The mathematics the Maya used to track the sky rested on a number system that was, in some ways, more advanced than anything in the rest of the world at that time. They counted in groups of 20 rather than 10, and they were among the first cultures on Earth to develop a true zero, represented by a small shell-shaped symbol. Their way of writing numbers allowed them to express very large figures with compact ease, and they put this ability to extraordinary use. The long count calendar, their system for tracking deep time, measured days from a starting point that corresponds to a date in the year 3114 before our era. Inscriptions at one Maya site extend this count to cover periods so vast that they dwarf the age of the universe itself. The sophistication of this system was a direct product of the Maya fascination with celestial cycles and their gift for the mathematics needed to track them. The Maya did not limit their attention to Venus. The Dresden Codex also contains tables for predicting eclipses, organized around a cycle of about 405 full moons, within which eclipses tend to repeat. Modern calculations have confirmed the reliability of these predictions. Like the Babylonians on the other side of the world, the Maya had discovered that eclipses follow patterns, and they used those patterns for both spiritual and political purposes. There is also evidence that they tracked the movements of Mars, Jupiter, and Saturn, though less of that evidence has survived. Astronomical alignments are woven into Maya buildings everywhere you look. At the city of Uxmal, a great palace is oriented not toward the other buildings of the city, but toward the farthest rising point of Venus, an alignment that only makes sense if you understand the sky. At Palenque, the Temple of the Inscriptions is positioned so that on the shortest day of the year, the setting sun appears to descend directly into the temple itself, symbolically entering the underworld, a fitting design for a building that houses the tomb of a great king. At Chichen Itza, the famous stepped pyramid creates a remarkable effect during the equinoxes, when triangular patches of light and shadow on the staircase produce the illusion of a serpent slithering down the steps. Whether this was carefully planned by the builders or is a happy accident of geometry has been debated for years, but it fits beautifully with the wider Maya practice of encoding the movements of the sky in stone. Beyond the Maya heartland, similar traditions flourished across the region. The Aztecs, who came later, created a massive stone disc over 3 meters across and weighing some 24 tons, carved with the epochs of their creation story, each age ending in a different catastrophe. The current age, they believed, would one day end in earthquakes. Every 52 years, at the end of a great calendar cycle, a ceremony was held in which all fires across the empire were put out. A new fire was kindled on a hilltop visible from the capital, and if it caught, the people knew the sun would rise again. The ceremony expressed, in the most vivid possible way, the belief that the universe required human participation to keep running. The destruction of this knowledge during the Spanish conquest is one of the great losses in the history of human thought. In 1562, a Spanish bishop ordered the burning of Maya books, calling them works of evil. Thousands of codices were destroyed. Only 4 are known to survive in the entire world today. The Dresden Codex, with its careful astronomical tables, is the most important of these, and it sits now in a library in Germany, far from the land where it was made. What was lost in those fires we will never know. But what survives is enough to tell us that the Maya developed one of the most precise and dedicated astronomical traditions in the world before the invention of the telescope. And the tradition did not entirely die. In the highlands of Guatemala and southern Mexico, calendar keepers have maintained the old 260-day cycle through centuries of colonial rule, passing the count from one generation to the next without a break. The sky for the Maya was not merely something to look at. It was the great wheel on which time itself turned. And in quiet villages far from any observatory, that wheel is still turning today. Let us travel now to another ancient land, where the sky was studied not from stone towers but from temple courtyards, and where a young mathematician once calculated the spinning of the Earth with an accuracy that would not be matched for 1,000 years. In the year 499 of our era, a 23-year-old mathematician in a city in northeastern India sat down and completed a book that would quietly change the course of astronomy. His name was Aryabhata, and his book contained a claim so bold that even some of his own students would refuse to accept it. The Earth, he wrote, was not standing still. It was spinning on its own axis once every day, and the apparent westward movement of the stars across the sky was not a real motion at all. It was an illusion, like the way trees on the riverbank seem to drift backward when you watch them from a boat floating gently downstream. This was not a vague suggestion or a passing thought. Aryabhata stated it plainly and backed it up with a calculation of how long one full spin of the Earth takes. His answer was 23 hours, 56 minutes, and just over 4 seconds. The figure that modern instruments give us is 23 hours, 56 minutes, and 4.091 seconds. His error was less than 1/10 of a second. More than 1,000 years before a Polish churchman named Copernicus would cautiously propose that the Earth moves around the Sun, a young Indian mathematician had already grasped, through reasoning and calculation alone, that the ground beneath his feet was in motion. The roots of Indian astronomy reach back much farther than Aryabhata. The oldest known Indian text devoted to the study of the sky was written perhaps around 1400 years before our era. It was not astronomy in the sense we would recognize today. It was a manual for figuring out exactly when to perform sacred rituals, because in the ancient tradition, timing was everything. If the priests performed the sacrifice at the wrong moment, the whole ceremony would fail, and the gods would not be pleased. The text opened with a line comparing astronomy to the finest jewel atop a serpent's head, the most honored of all the sacred sciences. This deep connection between watching the sky and honoring the divine would run through Indian astronomy for thousands of years, giving the study of the stars a prestige and support that kept it flourishing across the centuries. Over time, Indian astronomers absorbed ideas from other cultures. Through ancient trade routes and later through the Greek kingdoms established in the northwest of India, methods and concepts from Babylon and Greece made their way into Indian thought. Even some of the technical words used in Indian astronomy carry traces of their Greek origins. But the Indian scholars who received these ideas did not simply copy them. They transformed them with their own mathematical brilliance, and in many cases they surpassed the traditions they had learned from. The most important of their contributions was the number system we all use today, the system of 10 digits with a symbol for 0 and a way of writing numbers where the position of each digit determines its value. This system, developed in India during the early centuries of our era, was a tool of extraordinary power, and it would eventually reshape every branch of mathematics and science, astronomy above all. Aryabhata's own contributions went far beyond the spinning Earth. He calculated the length of the year with an error of only about 3 minutes. He correctly explained what causes eclipses, rejecting the old mythological story that a great demon swallows the sun or moon, and replacing it with the observation that the Earth's shadow falls on the moon during a lunar eclipse, and the moon blocks the sun during a solar eclipse. He developed tables of a mathematical function called the Sine, working in small, precise steps that were essential for calculating the positions of the stars and planets. His influence spread across India and through Arabic translations reached the scholars of the Islamic world. The great Muslim mathematician who gave us the word algebra referred to Indian astronomical methods, and the number system that Europeans would eventually adopt was known in the Islamic world as Hindu numerals, a name that acknowledged its true origin. A generation later, another towering figure of Indian astronomy appeared. Brahmagupta, born in 598 of our era in the western part of India, wrote a great astronomical treatise that both built upon and sharply criticized Aryabhata's work. He rejected the idea that the Earth spins, holding to the older view of a stationary Earth. Yet he engaged with Aryabhata's ideas in careful detail, naming him and debating him in passage after passage. Brahmagupta's own achievements were formidable. He refined methods for predicting eclipses and planetary positions, and he was the first person known to have written down the rules for doing arithmetic with zero and with negative numbers. His book was translated into Arabic at a royal court around 770 of our era, and that translation carried Indian mathematical astronomy directly into the heart of the Islamic intellectual world. The debate between those who followed Aryabhata in believing the Earth moves and those who followed Brahmagupta in believing it stands still would continue in India for centuries, never fully settled. Centuries later, a remarkable school of mathematicians and astronomers flourished in the southwestern corner of India. Working from roughly the 1400s onward, these scholars developed methods for calculating the values of certain mathematical functions using infinite sequences of smaller and smaller terms, techniques that would be independently discovered by European mathematicians 200 to 300 years later. Their primary motivation was to make astronomical calculations more precise, and in doing so they produced some of the most advanced mathematics anywhere in the world before the modern era. In the 18th century, Indian observational astronomy experienced one last magnificent flowering. A king named Jai Singh, dissatisfied with the accuracy of existing astronomical tables, embarked on an ambitious project. He built 5 enormous observatories across northern India, filled with stone instruments of astonishing size. The largest sundial in the city of Jaipur has a pointer that rises 88 feet into the air and can measure the time of day to within about 2 seconds. Other instruments were designed to track the positions of stars and planets with the naked eye at the highest possible accuracy. Jai Singh sent representatives to Europe, to Portugal and France to learn what Western astronomers were doing, and he drew on Indian, Islamic and European traditions alike in designing his observatories. By a quiet irony, by the time his magnificent instruments were finished, the telescope had already made naked-eye observation obsolete in Europe. His observatories were, in a sense, the most beautiful monuments to the end of an era. The story of Indian astronomy stretches across more than 3,000 years, from priests who needed the stars to tell them when to perform their sacrifices, to a young mathematician who realized the Earth was spinning, to a king who built instruments the size of buildings to read the sky more clearly. Along the way, Indian thinkers gave the world the number 0, the decimal system, and mathematical tools that traveled through the Islamic world and into the science of modern Europe. Aryabhata's quiet insight about the spinning Earth anticipated the Great Revolution in Western astronomy by over 1,000 years. And now, let us cross the widest ocean on Earth and listen to the story of people who carried their knowledge of the stars not in books or buildings, but in the extraordinary maps of their own memories. Sometime around the year 1000 of our era, a double-hulled canoe carrying perhaps 30 people pushed away from an island in the Central Pacific and headed out into open ocean. There was no compass on board, no chart, no instrument of any kind. The navigator, who may have been trained in the art of finding the way since childhood, stood at the back of the vessel and watched the sky. He carried his map entirely in his memory, the rising and setting points of more than 150 stars, the direction and rhythm of ocean swells, the flight paths of certain birds, and the subtle changes in cloud color and sea surface that hinted at land beyond the horizon. Using nothing but these cues, he would guide his canoe across hundreds of miles of featureless water to an island he could not yet see, with an accuracy that would astonish European explorers who encountered these seafarers centuries later. Can you picture that for a moment? No instruments, no written charts, nothing but the stars, the waves, and a lifetime of learning carried inside one person's mind. And yet the Polynesian navigators did not merely make one such voyage. Over a span of roughly 3,000 years, they settled virtually every inhabitable island in a vast triangle of ocean stretching from Hawaii in the north to New Zealand in the south and Easter Island in the east, an area covering nearly 16 million square miles. Some of the islands they found were tiny, low coral rings barely rising above the waves, invisible from more than a few miles away. Finding them required navigational accuracy measured in fractions of a degree, held steady over voyages lasting weeks. This is one of the most extraordinary feats of applied astronomy in all of human history. The heart of the system was the star compass, a mental map that divided the entire horizon into 32 sections, each about 11¼ degrees apart. Every section was linked to the rising or setting point of a particular star. As evening came and the stars appeared, the navigator would set a course toward a known star sitting in the right direction. As that star climbed higher and its position shifted, another star would rise to take its place at the correct bearing, and the navigator would shift his reference. This chain of stellar guideposts could carry the canoe through an entire night without a single moment of uncertainty. A master navigator from the small island of Satawal in what is now the Federated States of Micronesia had memorized the rising and setting points of more than 150 stars and could use this knowledge to navigate across the entire Pacific Ocean. He was among the last living links in an unbroken chain of knowledge stretching back over 2,000 years, and he spent the final decades of his life teaching what he knew to a younger generation before it could be lost forever. But the stars were only part of the toolkit. The ocean itself was a kind of map if you knew how to read it. Deep swells generated by distant storms travel thousands of miles across the Pacific in steady, reliable patterns. An experienced navigator could feel the direction and rhythm of these swells through the hull of the canoe, even while lying down at night. Islands disturbed these patterns in predictable ways, blocking swells on one side and bending them on the other, creating ripples and interference that a skilled navigator could detect from 50 miles away or more, long before the island itself could be seen. Low-lying atolls that were completely invisible from the surface of the water could be found by reading these wave signatures alone. Other clues included the behavior of certain seabirds, which fly out from land at dawn to fish and return in the evening, their paths pointing like arrows toward islands hidden over the horizon. The green glow of shallow lagoons could sometimes be seen reflected on the undersides of clouds. Even the trails of glowing sea creatures in the water at night could reveal the direction of ocean currents. One navigational concept used in the islands of Micronesia is worth pausing on, because it shows just how sophisticated this thinking was. In this system, the navigator imagines that the canoe is standing still and that it is the islands and the reference stars that are moving around it. The navigator pictures a reference island off to one side of the route and tracks which star it sits beneath as the voyage progresses. When the imaginary island has moved from under one star to under the next, one segment of the journey is complete. The navigator knows, of course, that the island is not actually moving. It is an abstract model, a way of simplifying the mental mathematics of position and progress. And it works with remarkable reliability. By the middle of the 20th century, these ancient arts were nearly extinct. Modern boats with engines and instruments had made star navigation unnecessary, and the old knowledge was fading with the last generation of trained navigators. Then, in 1976, something beautiful happened. A traditional double-hulled canoe named after a guiding star was launched from Hawaii for a 2,500-mile voyage to Tahiti, navigated entirely without instruments. The master navigator from Satawal guided the vessel using the old methods, and the voyage was a success. A young Hawaiian man who served as an apprentice on that journey became the first person of the modern era to learn the ancient art of wayfinding for long-distance ocean sailing. He went on to guide that same canoe on voyages spanning the entire Pacific, including a trip around the world completed between 2014 and 2017. The revival reconnected communities across the Pacific with traditions that had nearly been lost, and it proved beyond any doubt that the old methods were not quaint customs but fully working navigation systems of extraordinary power. On the far side of the Pacific, on the continent of Australia, another and even older tradition of sky knowledge had been quietly persisting for tens of thousands of years. The Aboriginal peoples of Australia, whose cultures stretch back more than 65,000 years, are arguably the oldest astronomers on Earth. Their way of reading the sky is different from anything we have encountered so far. While most traditions focus on the bright points of stars, connecting them into shapes and figures, Aboriginal sky knowledge pays equal attention to the dark spaces between the stars. The most well-known example is the Great Emu in the sky, a shape formed not by stars at all, but by the dark clouds of dust visible against the glowing band of the Milky Way. Its head sits near the Southern Cross, and its body stretches along the dark lane toward the constellation of Scorpius. When the emu appears to be running across the sky, it is time to hunt emus on the ground. When it appears to be sitting, it is time to gather their eggs. This is practical astronomy of the most intimate and beautiful kind, woven into the rhythms of daily survival. Other Aboriginal groups tracked the rising and setting of specific stars to predict when certain foods would be available, or watched the evening appearance of Venus to know when fish would come close to the surface. These traditions were passed down through stories, songs, and ceremonies across thousands of generations with a faithfulness that speaks to the deep structure of oral culture. Researchers working alongside Aboriginal communities have found that these traditions encode not only seasonal knowledge, but also records of unusual events in the sky, such as changes in the brightness of certain stars. Across the world, from the stone circles of the North American plains to the riverbanks of East Africa, indigenous peoples developed their own ways of reading the sky, each adapted to their own land, their own seasons, and their own needs. What all of these traditions share is a simple and profound truth. You do not need a telescope or a textbook to be an astronomer. You need only clear skies, a patient eye, and the desire to understand the world above you. And now, let us turn to a place where that desire took a new and very different form, where thinkers began to ask not just what happens in the sky, but why it happens at all. On the afternoon of a day in late May, 585 years before our era, two armies faced each other across a battlefield in what is now Turkey. The Medes and the Lydians had been fighting for 5 long years, and on this day they had drawn up their soldiers for yet another clash. But as the battle began, the sky grew dark. The sun vanished behind the moon, and the field was plunged into a strange and eerie twilight. Both armies, terrified by what they believed was a sign from the gods, put down their weapons and agreed to make peace. According to an ancient historian writing more than a century later, this solar eclipse had been predicted in advance by a philosopher named Thales, who lived in the Greek trading city of Miletus on the coast of Asia Minor. Whether Thales truly predicted the eclipse is something scholars have argued about for centuries. Modern astronomers have confirmed that a total solar eclipse did occur on that date and was visible from that part of the world. But how could he have known it was coming? Some have suggested that he learned of the eclipse cycle from Babylonian astronomers, which is possible given the busy trade connections between Miletus and the cities of the East. Others point out that the cycle the Babylonians used was much better at predicting eclipses of the moon than of the sun, which are only visible from narrow strips of the Earth's surface. Perhaps Thales simply made a general warning that an eclipse was likely within a certain window of time, and later storytellers sharpened the tale into a precise prediction. We may never know for certain, but the story itself, whether perfectly true or somewhat polished in the retelling, tells us something important. The Greeks gave credit for the prediction not to a priest or a king, but to a philosopher, a man who used reasoning to understand the natural world. And that shift from treating the sky as a message board of the gods to treating it as something that could be understood through thought and observation was one of the most important changes in the entire history of astronomy. The Greeks did not invent sky watching. People had been tracking the stars for tens of thousands of years before the first Greek philosopher was born. But the Greeks were among the first to ask a different kind of question. Not merely when will the next eclipse happen, but why does it happen at all? Thales was the first of a group of thinkers from the Greek cities along the coast of Asia Minor who sought natural explanations for natural events. Where the Babylonians had recorded heavenly omens and the Egyptians had tracked the stars for farming and ritual, these Ionian thinkers wanted to understand the universe as a system governed by understandable rules. Thales himself proposed that water was the basic substance from which everything in the world is made, an idea that is less interesting for what it claims than for the way it was arrived at. He was looking for a single, unifying explanation for the variety of nature, and he was using his own reasoning, not the words of a sacred text, to find it. His student Anaximander took this new way of thinking even further. He imagined the Earth as a short cylinder, floating freely in the center of the universe, held in place not by anything solid beneath it, but simply by the fact that it had no reason to fall in one direction rather than another. Think about that for a moment. This was a person living more than 2,500 years ago, proposing that the Earth hangs in empty space, supported by nothing but the logic of symmetry. It was wrong in many details, but the leap of imagination was extraordinary. He also suggested that the sun, moon, and stars were rings of fire hidden behind a kind of mist, with openings through which the fire could be seen, a creative attempt to explain what these glowing objects in the sky actually were. A generation or two later, a philosopher named Pythagoras, who settled in southern Italy and founded a school of followers devoted to mathematics and philosophy, is traditionally credited with arguing that the Earth is a sphere. The evidence he offered, or that was later offered in his name, included the observation that ships sailing away over the sea disappear hull first, as though sinking over a curve, that the Earth casts a round shadow on the moon during eclipses, and that the sphere is the most perfect of all geometric shapes and therefore the form most fitting for a heavenly body. Whether Pythagoras himself made all these arguments, or whether his later followers put words in his mouth, is impossible to say with certainty. But by the 500s before our era, the idea of a round Earth was widely accepted among Greek thinkers. The followers of Pythagoras also believed that the universe was governed by mathematical harmony, that the planets themselves produced a kind of music as they moved through the sky, too subtle for human ears to hear. This deep conviction that mathematical patterns lie at the heart of physical reality would turn out to be one of the most important ideas in the history of human thought. The most detailed attempt to build a working model of the heavens before the age of telescopes was made by a man named Eudoxus, who lived in the 4th century before our era and was a contemporary of the great philosopher Plato. Eudoxus proposed that each heavenly body, the sun, the moon, and each of the 5 planets visible to the naked eye, was carried on a set of invisible nested spheres all centered on the Earth. By adjusting the number, tilt, and speed of these spheres, he could roughly reproduce the movements that astronomers actually observed in the sky, including the strange backward loops that the outer planets sometimes appear to make. His system needed 27 spheres in all. And while it could mimic some of the patterns in the sky, it could not explain why the planets sometimes looked brighter and sometimes dimmer, which would naturally happen if they were changing their distance from us. Then came Aristotle, perhaps the most influential thinker in the history of Western civilization. Aristotle took the mathematical model of Eudoxus and turned it into a complete picture of the universe. For Aristotle, the spheres were not just mathematical aids. They were real, physical objects made of a special, flawless substance that filled the heavens, a fifth element beyond Earth: water, air, and fire. The universe was divided into two realms. Below the moon, everything was made of the four earthly elements and was subject to change and decay. Above the moon, everything was made of this perfect substance and was eternal and unchanging. The Earth sat at the very center of everything, because heavy things naturally fall toward the center, and the Earth, being the heaviest, had settled at the lowest point. The stars did not change because change was a property of earthly matter, not of the heavens. It was a beautiful system, logical and satisfying, and it seemed to match everything people could see. The stars did appear unchanging. The planets did appear to move in circles, and the Earth certainly felt as though it was standing still. Aristotle's picture of the cosmos would dominate thinking across the Greek, Roman, Islamic, and Christian worlds for nearly 2,000 years. Scholars would build their theologies around it. Opponents of new ideas would quote him as the final authority. His crystal spheres became the very architecture of the medieval universe. The trouble, of course, was that he was wrong, but the world was not ready to know that yet, and it would take a very long time and a great many patient observers before anyone could prove it. But now, the philosopher's sky, beautiful, logical, and mistaken, held firm. Let us move forward now to a time when Greek thinkers stopped only imagining the shape of the universe and began, for the first time, to measure it. Around 270 years before our era, on the island of Samos in the eastern Aegean Sea, a mathematician named Aristarchus sat working through a problem that no one had ever solved. He was trying to figure out how far away the sun and the moon are, and how large they are compared to the Earth, using nothing more than the geometry of shadows and the timing of eclipses. His method was beautifully simple. When the moon is exactly half lit, the angle between the sun, the moon, and the observer on Earth forms a right triangle. By measuring that angle, you can work out how much farther away the sun is than the moon. His measurement of the angle was not very accurate, and it led him to conclude that the sun was about 20 times farther than the moon, when the true ratio is closer to 400. But the logic behind his method was flawless, and the conclusion he drew from even his rough numbers was extraordinary. The sun, he reasoned, must be much larger than the Earth. And if the sun was the larger body, it made no sense for the larger to circle the smaller. And so Aristarchus proposed something that would not be proposed again for another 1800 years. He said that the Earth moves around the sun, not the other way around. The Earth, he argued, revolves around the sun once a year and spins on its own axis once a day. And the stars are fixed on a distant sphere so incredibly far away that any shift in their apparent positions caused by the Earth's movement would be too small to detect. This was the same argument in all its essentials that Copernicus would make in the 1500s. But Aristarchus made it first, and he made it alone in a world that was not ready to hear it. Why was his idea rejected? There were several reasons, and they were not foolish. The most powerful was a simple observational test. If the Earth is really moving around the sun, then the nearby stars should appear to shift their positions slightly as we view them from different points in our orbit, the way a nearby tree seems to shift against the distant hills when you move your head from side to side. No one could detect any such shift. Aristarchus had an answer for this, that the stars were simply too far away for the shift to be visible, and he was right, but no one could prove it at the time. That tiny shift in the stars would not actually be measured until 1838, more than 2,000 years later. There were also arguments from everyday experience. If the Earth is spinning, then a stone dropped from a tall tower should land slightly to the west of the base because the ground beneath it would have moved while the stone was falling. The stone does not do this. It falls straight down. It would take the discovery of a concept called inertia many centuries later to explain why. And so Aristarchus's beautiful idea was set aside, remembered but not adopted, a bright spark that flickered and went out. But the spirit of measurement that produced it did not die. A generation later, another extraordinary thinker made a measurement that would be remembered as one of the most elegant experiments in all of ancient science. His name was Eratosthenes, and he was the chief librarian at the Great Library of Alexandria, one of the most remarkable minds of his era. Eratosthenes had learned something interesting about the city of Syene, far to the south. At noon on the longest day of the year, the sun stood directly overhead in Syene. A straight stick cast no shadow at all, and sunlight shone straight down to the bottom of a deep well without touching the sides. But in Alexandria, about 5,000 stadia to the north, the sun at the very same moment was not quite overhead. A vertical stick there did cast a shadow, and Eratosthenes measured the angle of that shadow at about 7 degrees, which is roughly 1/50th of a full circle. Now, if the Earth is a sphere and the sun's rays are essentially parallel, which they very nearly are given how far away the sun is, then the distance between Syene and Alexandria must be about 1/50th of the total distance around the Earth. Multiply that distance by 50 and you have the circumference of the Earth. The answer Eratosthenes got, depending on exactly how we convert his ancient unit of measurement into modern terms, comes out to somewhere between 39,000 and 46,000 kilometers. The true figure, measured by satellites, is just over 40,000 kilometers. Using nothing but a stick, a shadow, and a stroke of brilliant reasoning, a librarian in ancient Egypt came within a few percent of the right answer. The greatest observational astronomer of the ancient world, however, was a man who worked on the island of Rhodes in the 2nd century before our era. His name was Hipparchus, and although almost none of his original writings survive, his achievements can be pieced together from the later work of others who built on his foundations. Hipparchus compiled a catalogue of more than 850 stars, giving each one a position in the sky and a brightness rating on a scale from 1 to 6, with 1 being the brightest and 6 the faintest visible to the naked eye. That brightness scale, with modifications, is still used by astronomers today. He measured the length of the year, the time from one spring equinox to the next, to within about 6.5 minutes of the modern value. And he made what may be the single most important observational discovery in all of ancient astronomy. By comparing his own measurements of star positions with observations made about 150 years earlier by other astronomers, Hipparchus noticed that certain stars near the path of the sun had shifted slightly. After careful thought, he concluded that the entire framework of the sky was slowly rotating, that the points where the sun crosses the equator each spring and autumn were gradually drifting westward. We now call this precession, and we know that it is caused by a slow wobble in the Earth's spinning axis, like the wobble of a toy top completing one full cycle every 26,000 years or so. Hipparchus could not have known the cause, but he identified the effect with a precision that speaks to extraordinary patience and skill. And then there is one more marvel from this era that deserves a place in our story. In the year 1901, divers exploring a Roman shipwreck near a small Greek island brought up a corroded lump of bronze. It would take decades for anyone to realize what it was. Inside the lump was a mechanism of interlocking gears, at least 30 of them, housed in a wooden case about the size of a shoebox. When reconstructed, it turned out to be a kind of ancient computer capable of calculating the positions of the sun, moon, and planets, the phases of the moon, and the timing of eclipses. Nothing of similar complexity would be built in Europe for over 1,000 years. It is a humbling reminder that the ancient world was capable of things we have barely begun to appreciate, and that knowledge once gained can be lost for centuries before it is found again. The age of Aristarchus, Eratosthenes, and Hipparchus was the golden age of ancient astronomy. In the space of 2 centuries, one thinker proposed that the Earth orbits the Sun, another measured the size of the Earth with a stick and a shadow, and a third catalogued the stars and discovered the slow wobble of the heavens. The knowledge they created would be gathered up, organized, and given a lasting form by the man we will meet next, a quiet scholar in Alexandria who wrote the most influential astronomy textbook the world has ever known. In the Egyptian city of Alexandria, sometime around 150 years into our era, a man named Claudius Ptolemy sat writing what would become the most influential science book in history. He called it simply the Mathematical Collection, but the world would come to know it by an Arabic name meaning the greatest, a title that stuck because for more than 1,000 years, no one could seriously argue with it. In 13 carefully organized sections, Ptolemy gathered together 5 centuries of Greek skywatching and mathematical theory and wove them into a single, complete system that could predict where the sun, the moon, and every visible planet would be in the sky on any given night. His system placed the Earth at the center of everything, and it held that position in the minds of astronomers, philosophers, and religious thinkers for more than 1,200 years. No other scientific work has ever dominated its field for so long. Ptolemy was not a daring original thinker in the way that Aristarchus or Hipparchus had been. His particular gift was something different and in some ways equally valuable. He was a compiler and an organizer of extraordinary skill. He took the observations of the astronomers who came before him, corrected their errors where he could, added observations of his own, and embedded everything in a mathematical framework so elegant and so useful that no one found a reason to abandon it for more than a millennium. His book was not just a work of theory. It was also a practical manual, filled with worked examples showing step by step how to calculate the position of a planet for any date you chose. It was, in the truest sense, both a map and a set of instructions for the sky. The way Ptolemy explained the movement of the planets was clever and, in its own way, beautiful. Each planet in his model traveled on a small circle, the center of which in turn traveled along a much larger circle centered near, but not exactly at the Earth. By adjusting the sizes, speeds, and tilts of these circles, Ptolemy could make his model match what astronomers actually saw in the sky with quite impressive accuracy. He also introduced a special point, set at a precise distance from the center of the larger circle, from which the motion of the smaller circle appeared perfectly steady and uniform. This was his most ingenious trick, and also his most controversial one. It worked beautifully for making predictions, but it bothered many later astronomers because it meant that the motion was not truly uniform when seen from the natural center of the circle. That discomfort would simmer for centuries, and it would eventually become one of the reasons people began to look for a different model of the heavens entirely. But for the moment, the system worked, and that was what mattered most. It could tell you where Mars would be next month, where Venus would appear at dawn 3 years from now, when the next eclipse would fall. The predictions were accurate to within a few degrees, which was more than good enough for the calendar makers, the navigators, and the astrologers, who were the main users of astronomical tables in the ancient world. And this practical success was the system's most powerful defense. As long as it could deliver useful answers, objections about whether the underlying picture was physically real seemed rather beside the point. Ptolemy's star catalogue, which filled 2 full sections of his great book, listed over 1,000 stars arranged into 48 groups that we still call constellations. He rated the brightness of each star on a scale from 1 to 6, and that scale, refined but not fundamentally changed, is still the one astronomers use today when they talk about the brightness of a star. The 48 constellations he described remain the core of the 88 constellations officially recognized around the world. Every time you look up on a clear night and someone points out Orion or the Great Bear or the Scorpion, you are using a map that Ptolemy helped to draw. When the Roman Empire fragmented and classical learning faded in Western Europe, Ptolemy's great book survived because it traveled east. It was translated into Arabic more than once and became the foundation of astronomical education across the Islamic world. Arab scholars corrected some of his errors, improved some of his measurements, and identified weaknesses in his geometric methods, but they did not replace the fundamental picture of an Earth-centered universe. When his book was translated back into Latin in the 1200s by a scholar working in the Spanish city of Toledo, it reintroduced European thinkers to a level of mathematical astronomy they had not possessed for 700 years. The effect was transformative, like suddenly gaining access to a vast library that had been locked away for centuries. Ptolemy also wrote about astrology, and that work proved nearly as influential as his astronomy. His astrological text provided the theoretical foundation for the practice of reading the stars to predict human events, and it found an eager audience that lasted for over 1,000 years. Astrologers needed accurate planetary positions to cast their horoscopes, and so the demand for better horoscopes drove the demand for better astronomical tables, which in turn drove the demand for better observations and better mathematical methods. In a quiet, almost accidental way, astrology helped keep astronomy alive during centuries when purely scientific curiosity might not have been enough to sustain it. The system Ptolemy built survived for so long, not because no one ever questioned it, but because every question that arose could be handled by making small adjustments to the model without throwing away the whole framework. If a planet was not quite where the tables said it should be, you could tweak the size of one of the circles or adjust the speed of another and bring the predictions back in line. This flexibility made the system remarkably hard to disprove. It was not until someone came along with a completely different picture of the heavens, one that offered similar accuracy with a fundamentally different geometry, that the Ptolemaic system finally faced a real rival. And even then, the transition would take more than a century. Ptolemy himself remains a somewhat mysterious figure. We know almost nothing about his personal life. His name suggests a man who lived at the crossing point of Greek and Egyptian cultures in the busy cosmopolitan city of Roman Alexandria. His legacy is the universe that bears his name, the Earth at the center, the planets on their graceful circles within circles, the stars fixed on the outermost shell, and the mathematical machinery that held everything in its place. That universe was beautiful, orderly, and centered on us. It was also, as we shall eventually see, quite wrong. But it was the best picture anyone had for a very long time. And when the picture that finally replaced it was built, it was constructed, stone by stone, on the foundations that Ptolemy had laid. And now the story takes a quiet turn eastward to a golden age of learning where scholars not only preserved this ancient knowledge, but lifted it to heights that Ptolemy himself could not have imagined. In the year 829 of our era, the ruler of the vast Islamic empire, a caliph named Al-Ma'mun, ordered the construction of an astronomical observatory in Baghdad. It was the first observatory in the Islamic world to be funded by the state, and it was attached to a remarkable institution called the House of Wisdom, which Al-Ma'mun had expanded into the greatest center of learning on earth. Within its walls, scholars translated the works of the ancient Greeks, the Persians, and the Indians into Arabic, creating a storehouse of human knowledge that would sustain scientific progress for 500 years. The chief translator of the age was said to have been paid the weight of his finished manuscripts in gold, a measure of how highly this work was valued. Among the first and most important texts to be translated was Ptolemy's great book on astronomy, and its arrival in Arabic set off a wave of astronomical work that would not merely preserve the Greek tradition, but dramatically advance it. The Islamic engagement with astronomy was driven by both the love of knowledge and the needs of daily life. The faith required its followers to pray 5 times each day at moments determined by the position of the sun in the sky. It required them to face toward the holy city of Mecca from wherever they happened to be on the globe. And it required them to mark the beginning and end of the month of fasting by the sighting of the thin crescent moon. Each of these requirements posed a real astronomical challenge, and meeting them pushed scholars to develop new mathematical tools and new instruments of observation. Figuring out the direction of Mecca from cities scattered across 3 continents was a problem in the geometry of spheres, and solving it led Islamic mathematicians to develop the functions of trigonometry, the sine, the cosine, and the tangent, in forms that went far beyond anything the Greeks had achieved. The astrolabe, a beautiful brass instrument perfected in the Islamic world, became the all-purpose tool of the medieval astronomer. With a single astrolabe, you could tell the time, find the direction of Mecca, measure the height of a star above the horizon, and solve dozens of other astronomical problems. One of the great early figures of Islamic science was a mathematician whose name gave us the word algorithm. He compiled astronomical tables that blended methods from India, Persia, and Greece into a single practical system for calculating the positions of the planets. His tables were partly based on Indian sources that had been brought to Baghdad by visiting scholars in the 8th century, a reminder of how freely knowledge flowed along the trade routes of the medieval world. This format, a set of tables accompanied by instructions for their use, became the standard way of publishing astronomical work in the Islamic world, and hundreds of such table sets were produced over the following centuries, each improving on those that came before. A later astronomer, working in the city of Raqqa in northern Syria, produced measurements of the length of the year and the tilt of the Earth's axis that were more accurate than anything Ptolemy had achieved. His work was still being cited by Copernicus over 600 years later. But the most important challenge to the Ptolemaic system to come from the Islamic world arose at an observatory built in the hills of northwestern Persia in the 1250s. The observatory was founded under the patronage of a Mongol ruler who, having recently destroyed much of Baghdad and its libraries, now wanted accurate horoscopes for himself. He commissioned a brilliant Persian scholar to design and direct the observatory, and the result was a gathering of some of the finest astronomical minds of the age, drawn from across the Islamic world and even including a Chinese astronomer, a testament to the vast reach of the Mongol Empire. The instruments they used were among the finest ever built up to that time, and the observations they made set a new standard for accuracy in the medieval world. At this observatory, a mathematical device was developed that would prove to be one of the most important innovations in the history of astronomy. It was a way of producing straight-line motion from the combination of 2 circular motions, a geometric trick that solved a specific and long-standing problem with Ptolemy's system. Many astronomers had been troubled by a point in Ptolemy's model from which planetary motion appeared uniform, even though that point was not the natural center of the planet's path. This felt wrong, a violation of the ancient principle that heavenly motion should be smooth and circular. The new device offered an elegant alternative, preserving the appearance of smooth circular motion while reproducing exactly the same observable effects. It was the most beautiful mathematical innovation in astronomy since Ptolemy himself, and it showed that Islamic astronomers were not simply curators of Greek knowledge but creative thinkers in their own right. And here is something worth pausing on. Nearly 3 centuries later, when Copernicus wrote his famous book, placing the sun at the center of the universe, he used this very same mathematical device. His model for the motion of the moon was virtually identical to one developed by a 14th century astronomer who worked as the official timekeeper at the Great Mosque in Damascus. How these techniques traveled from the Islamic world to Copernicus is one of the great unsolved puzzles in the history of science. One possible route runs through scholars in the Eastern Mediterranean who had access to Arabic texts and who were in contact with Italian thinkers during the very years that Copernicus was studying in Italy. Whether through direct borrowing or independent reinvention, the mathematical foundations of the revolution that Copernicus would start had roots in the Islamic world. In the city of Samarkand, in Central Asia, a prince who was also a serious astronomer built an observatory in the 1420s that would produce the most accurate star catalogue since the ancient world. He was unusual among rulers in that he reportedly spent nights at the observatory making observations alongside his staff. His main instrument was enormous, carved into the side of a hill with a radius of about 36 meters, and it could measure the positions of stars with a precision that would not be surpassed until the late 1500s. The catalogue he produced listed the positions of over 1,000 stars with an accuracy that exceeded not only Ptolemy's ancient work, but also the later measurements of Copernicus. This remarkable astronomer prince was murdered by his own son in a struggle for power, and his observatory fell into ruin, but his catalogue survived, carried by scholars and travelers across continents, and was eventually translated into Latin, where it entered the mainstream of European science. The gifts of Islamic astronomy to the world are written into the very language we use to talk about the sky. Words like zenith, nadir, and azimuth are Arabic. So are the names of many of the brightest stars: Aldebaran, Betelgeuse, Rigel, Vega, Altair, all echoes of the centuries when Arabic was the international language of science. Islamic astronomers preserved the Greek heritage during a time when it was largely forgotten in Western Europe. They corrected it, refined it, and added new tools and techniques of their own. The transmission of this knowledge to Europe through Spain, through Sicily, and through the scholars of the Eastern Mediterranean was one of the most important intellectual transfers in all of human history. The astronomical revolution that would soon unfold in Europe is simply impossible to understand without it. And with that, let us cross back into Europe to a time often called the Dark Ages, and see that the sky above those centuries was not nearly so dark as its reputation suggests. In a stone room in a monastery in what is now northeastern Switzerland, around the year 850, a monk knelt in the darkness of the early morning hours and watched the sky through a narrow window. He could not glance at a clock, because no such thing existed yet. Instead, he was waiting for a particular star to reach a certain point on the horizon. When it did, he would ring the bell that summoned his brothers to the first prayer of the day. For this monk, the knowledge of the stars was not a luxury or an intellectual hobby. It was the technology of prayer, the only reliable way to keep the sacred schedule of worship when nothing else could tell the time. Guides for this purpose circulated among monasteries, describing which groups of stars to watch at each hour of the night in each season. The daily rhythm of monastic life with its 7 appointed times of prayer was held together by the quiet turning of the sky above. Medieval Europe has long been called a dark age for science, a time when the great discoveries of the ancient world were forgotten and nothing new was learned. But that picture is misleading, and it is worth setting it right. While it is true that Western Europe lost touch with the most advanced Greek astronomy for several centuries, the watching of the sky never stopped. Monks tracked the stars to time their prayers. Scholars worked out the complex mathematics needed to calculate the date of Easter. And a small but dedicated community of thinkers preserved what they could of the old knowledge and slowly began to build upon it. The calculation of Easter was, in fact, the single most important astronomical problem in medieval Christendom, and it was far more difficult than you might expect. Easter falls on the first Sunday after the first full moon following the spring equinox, which means you need to know both the solar calendar and the lunar calendar and be able to reconcile the two. This is not a simple task, because the moon's cycle of phases does not divide evenly into the solar year, and small errors accumulate over time. Working out when Easter would fall required careful arithmetic that occupied some of the finest minds in the medieval church. One of those minds belonged to a monk named Bede, who lived at a monastery in the north of England in the early 700s. His book on the reckoning of time became the standard reference on the subject for centuries. In it, he explained the 19-year cycle after which the phases of the moon fall on the same dates of the solar calendar, described the methods for computing Easter, and discussed the shape of the Earth and the influence of the moon on the tides, demonstrating that not all ancient scientific knowledge had been lost. Bede knew the Earth was round, and he could explain why. The great transformation of medieval European astronomy began in the 1100s and 1200s when scholars gained access to a flood of knowledge that had been preserved and improved in the Islamic world. The center of this intellectual transfer was the Spanish city of Toledo, which had recently been retaken from its Muslim rulers and where scholars from across Europe came to learn Arabic and translate the treasures of Islamic science into Latin. One Italian scholar who settled in Toledo specifically to learn Arabic is credited with translating more than 70 works on his own, including Ptolemy's great book on astronomy and the astronomical tables of Islamic mathematicians. By the early 1200s, European scholars had access for the first time in 700 years to the full mathematical power of ancient Greek astronomy, enriched by centuries of Islamic improvement. The impact on European intellectual life was enormous, like suddenly being given the keys to a vast library that had been locked shut for generations. The most widely read astronomy textbook of the medieval period was a short, clear introduction to the Earth-centered universe, written around 1230. It drew on Ptolemy, Aristotle, and Arabic sources to present a straightforward picture of the heavens, with the spherical Earth at the center surrounded by the nested spheres carrying the moon, the sun, the planets, and the fixed stars. This little book was adopted as a standard text in universities across Europe and remained in use for over 400 years, going through hundreds of handwritten copies and, after the invention of printing, at least 200 printed editions. Every educated person in late medieval Europe would have been familiar with its description of the celestial spheres and the basic principles of the sky. The most ambitious astronomical project of the medieval period was a set of planetary tables commissioned by King Alfonso X of Castile, known as Alfonso the Wise, in the mid-1200s. Prepared under the direction of two Jewish scholars in Toledo, the tables provided the mathematical tools to calculate the positions of the sun, moon, and planets for any date. Alfonso himself is said to have joked that if God had consulted him during the creation, he might have suggested a simpler arrangement of the heavens, a remark that captures the genuine difficulty of working with the circles within circles of Ptolemy's system. A revised version of these tables prepared in Paris in the 1320s spread rapidly and became the standard planetary tables across Europe for the next 3 centuries. But the medieval period was not merely a time of receiving and transmitting old knowledge. Within the growing universities of Europe, thinkers were beginning to question the foundations of the ancient system. A philosopher at the University of Paris in the 1300s developed a new idea about motion that departed significantly from Aristotle. He proposed that when you throw an object, the act of throwing gives it an internal force that keeps it moving even after your hand lets go. This may sound obvious to us today, but it contradicted Aristotle's teaching that a moving object requires a constant push from outside to keep going. This thinker applied his idea to the heavens, suggesting that God had given the celestial spheres an initial push at the moment of creation, and that they continued to spin because there was nothing to slow them down. This was, in a quiet way, an early version of the idea that would eventually become one of the most fundamental principles in all of physics, the principle that a moving object will keep moving unless something stops it. One of his students went even further. Writing in the late 1300s, he argued that there was no conclusive proof that the Earth was standing still, and that many of the arguments against its rotation could be answered. He showed that if the Earth was spinning, everything on its surface, including the air, the oceans, and every object you might throw, would share that spin, and so you would never notice it. He ultimately concluded that the Earth was probably not moving out of respect for the teachings of Scripture, but his willingness to seriously consider the possibility shows that the intellectual ground was being prepared for a revolution long before the revolutionary arrived. Another medieval thinker, a Franciscan friar writing in the 1260s, argued passionately for the importance of careful observation and mathematical methods in the study of nature. He pointed out that the calendar then in use had accumulated an error of several days and called for it to be corrected, a reform that would not actually happen until 1582, more than 300 years later. His voice was one of many that helped create a climate in which precise observation and mathematical reasoning were increasingly valued. Medieval European astronomy then was not the empty wasteland it is often made out to be. It was a time of quiet growth, of seeds being planted that would not flower for centuries. The monks who watched the stars, the scholars who translated Arabic texts, the professors who dared to question Aristotle, all of them played a part in the long, slow process that would eventually lead to one of the greatest upheavals in the history of human thought. And that upheaval began, as such things often do, with a single quiet man who spent decades thinking about a problem before he dared to share his answer. In a small town on the coast of the Baltic Sea, in a province of Poland called Warmia, a middle-aged churchman climbed the stairs to a small tower he had turned into an observatory. The year was perhaps 1520, and the man, Nicolaus Copernicus, had been working on the same problem for nearly 20 years. He had concluded, through careful mathematics, that the sun, not the Earth, sat at the center of the planetary system, and he had built a complete geometric model to show it. But he could not bring himself to publish. He knew what the reaction would be, not just from the church, but from the scholars and professors who had been teaching the Earth-centered model for centuries. And so he worked on, refining his calculations, adding observations, putting off the moment of revelation year after year. The tower where he worked still stands today, a modest brick structure barely 20 feet across, an unlikely birthplace for one of the greatest changes in the history of human thought. Copernicus was born in 1473 in a Polish town along the Vistula River. His father, a prosperous copper merchant, died when he was 10, and an uncle who was a bishop took charge of his education. That uncle's support secured Copernicus a comfortable position in the church, one that came with a steady income and enough free time for scholarly pursuits. He studied first in Poland, where he learned the basics of the Earth-centered astronomy that everyone accepted. Then he traveled to Italy and spent nearly a decade at the universities there, studying law, medicine, Greek, and astronomy. It was in Italy, surrounded by the intellectual ferment of the Renaissance, that Copernicus may have first begun to suspect that Ptolemy's ancient model was not the only way to explain the movements of the planets. Around 1514, Copernicus put his ideas into writing for the first time in a short document that he shared privately with a handful of trusted friends. In it, he laid out 7 bold statements. The sun, he said, was near the center of the universe. The Earth was just another planet, orbiting the sun once each year. What appeared to be the movement of the sun across the sky was actually caused by the Earth spinning on its own axis. And the strange backward loops that the planets sometimes seemed to trace in the sky were not real motions at all, but an illusion caused by the combination of the Earth's movement with theirs. This short document circulated quietly among astronomers and churchmen. By 1533, a summary of Copernicus's ideas had been presented to the Pope himself, and the response was one of interest rather than alarm. But the full version of the work, the great book that would lay out the mathematics in exhaustive detail, sat on his desk for years, essentially finished but unpublished. Copernicus was a cautious man by nature, and his hesitation had many roots. He feared ridicule from scholars who would dismiss his theory as absurd. He knew that his model, despite its elegance, did not actually predict the positions of the planets much better than the old system, because he had kept the assumption of circular orbits and still needed many of the same mathematical adjustments that Ptolemy had used. In fact, his model required slightly more of these adjustments than Ptolemy's, which weakened his claim that it was simpler. And he may have worried about the theological implications of removing the Earth from its place at the center of creation. The situation changed in 1539, when a young mathematician from a German university arrived in Warmia, eager to study with the aging master. This young man, Georg Joachim Rheticus, read the unpublished manuscript and was electrified. He quickly wrote a summary of its arguments and published it, and the response from certain mathematical circles was enthusiastic. His energy and persistence eventually persuaded the reluctant Copernicus to let the full work go to print. The book was sent to a publisher in Nuremberg, but its printing was overseen by a theologian who, without Copernicus's knowledge or permission, added a preface claiming that the entire theory was merely a mathematical exercise, useful for calculation but not necessarily a picture of how things really are. This preface softened the book's impact and confused readers for decades, because no one could be sure whether the author intended his theory to be taken as truth or as a convenient fiction. The deception was not exposed until the early 1600s. The book, titled On the Revolutions of the Celestial Spheres, was published in 1543. According to a famous story, a copy was placed in Copernicus's hands a few days after he had suffered a stroke and lost consciousness. He is said to have awakened just long enough to see his life's work in print before dying on May the 24th, at the age of 70. The story may be embellished, but it has become one of the most poignant scenes in the history of science. The immediate reaction to the book was quieter than you might expect. It was a dense and difficult work, accessible only to specialists, and the initial printing was probably around 400 copies. Most of those who read it were more interested in its mathematical methods than in its bold claim that the Earth moves. An astronomer in Wittenberg used the new data to compile improved planetary tables, which helped spread the techniques of Copernicus across Europe, even though this same astronomer did not accept that the Earth actually orbits the Sun. The system still relied on circular orbits and required nearly as many mathematical adjustments as Ptolemy's, and its predictions were not dramatically better. Without strong new evidence, most scholars found the idea of a moving Earth too radical to accept. Yet the seed had been planted. Over the next century, the idea that the Sun stands at the center would attract brilliant supporters and provoke fierce opponents. It would inspire new observations, new mathematics, and ultimately an entirely new understanding of what the universe is. Copernicus himself might have been surprised by the scale of the revolution that carries his name. He was a conservative man, a churchman who believed he was restoring the ancient harmony of the heavens, not overthrowing it. He dedicated his great book to the Pope and framed his arguments in the language of mathematical elegance rather than physical truth. But the consequences of his work would reach far beyond anything he had imagined. And now, let us meet the man who would take the next great step, a flamboyant Danish nobleman with a brass nose and the most precise eyes in Europe. On the night of November the 11th, 1572, a 25-year-old Danish nobleman stepped out of his laboratory and looked up at the familiar constellation of Cassiopeia. What he saw made him doubt his own eyes. A star that had not been there before was blazing in the sky, brighter than Venus, brighter than anything except the moon. He rubbed his eyes, called his servants outside to confirm what he was seeing, and then spent the next 18 months making the most careful observations of his life. He measured the new star's position again and again using instruments of his own design, and he found that it did not move in relation to the stars around it. This meant it was not a comet, not a shooting star, not a trick of the atmosphere. It was something genuinely far away, in the realm of the fixed stars themselves. And that was devastating news for anyone who believed, as the followers of Aristotle did, that the heavens beyond the moon were perfect and could never change. The young man's name was Tycho Brahe, and his observation of that new star, published the following year, made him the most famous astronomer in Europe. The star itself was the explosion of a dying sun, one of only a handful of such events visible to the naked eye in the past 2,000 years. Its faint remains can still be seen today through modern telescopes. Tycho Brahe was as colorful in his personal life as he was meticulous in his observations. Born into one of the most powerful noble families in Denmark in 1546, he was taken as an infant by a childless uncle and raised in that uncle's household. an arrangement so unusual that it speaks to a different era's sense of family. He studied at several universities where he became fascinated by astronomy after witnessing a solar eclipse at the age of 14 and being struck by the fact that it had been predicted in advance. At the University of Rostock, he fought a duel with another student, reportedly over who was the better mathematician. The fight cost Tycho the bridge of his nose, which was sliced off by his opponent's sword. For the rest of his life, he wore a replacement piece made of brass for everyday use and of gold and silver for special occasions. The King of Denmark, impressed by Tycho's growing reputation, granted him an entire island in the strait between Denmark and Sweden, along with a generous annual income. There, beginning in 1576, Tycho built the most elaborate astronomical research facility the world had ever seen. It was a castle designed for the stars, equipped with purpose-built instruments, a printing press for publishing results, a chemical laboratory, and gardens laid out in precise geometric patterns. When this first observatory proved not quite enough, he built a second one nearby, with instruments sunk into pits below ground level, covered by rotating roofs to protect them from the wind. The instruments he designed and built were the finest of the age. His great measuring arc, fixed to a wall aligned exactly with the north-south line, could determine the position of a star in the sky with an accuracy roughly 10 times better than anything that had come before. He understood that every measurement is affected by the bending of light in the atmosphere, by tiny flaws in the instruments, and by simple human error, and he developed careful methods to account for all of these, an approach to the problem of accuracy that was far ahead of its time. Over 20 years on that island, Tycho compiled the most extensive and precise set of astronomical observations in history. Night after night, year after year, he recorded the positions of the sun, the moon, the planets, and the stars with a patience and a precision that no one had ever matched. His observations of Mars were particularly important. He tracked the planet's position continuously, building up a collection of data so precise that it would reveal patterns invisible to every previous observer. He also observed a great comet in 1577 and proved, through careful measurement, that it was located far beyond the moon, another blow to the old idea that the heavens are unchanging. Yet for all his brilliance as an observer, Tycho himself never accepted the idea that the Earth moves around the Sun. Instead, he proposed a compromise. In his model, the Sun and Moon orbited the Earth, but the other 5 planets orbited the Sun. This kept the Earth at the center of things while capturing some of the mathematical advantages of the Sun-centered system. It was a reasonable position for a man who had not yet seen proof that the Earth moves, and it attracted a following, especially among scholars who were reluctant to challenge church teachings. Tycho's time on his island ended badly. After his royal patron died, the new king reduced his funding, and Tycho's own difficult personality had worn out his welcome with the local people. In 1597, he left Denmark in anger and eventually settled in Prague under the patronage of the Holy Roman Emperor, a ruler known for his interest in the mysterious and the scientific. In Prague, Tycho hired a young German mathematician named Johannes Kepler as his assistant. The partnership between these two men would prove to be one of the most important in the history of science, but it was also one of the most troubled. Tycho guarded his precious data jealously. He assigned Kepler to work on the problem of Mars, but gave him the numbers only in small portions, keeping the young man dependent and frustrated. Tycho died in Prague on October 24, 1601, at the age of 54. The circumstances of his death have fascinated people for centuries. He had attended a banquet where he reportedly drank a great deal and, out of a sense of etiquette, refused to excuse himself from the table when he needed to. The resulting illness proved fatal within days. For a long time, there were rumors of poisoning, but modern analysis of his remains has found nothing to support that theory. After Tycho's death, Kepler gained access to the precious Mars observations, partly through careful negotiation with Tycho's family, and partly through what he himself admitted was a certain degree of taking what he needed. With those numbers in hand, he set to work on a problem that would consume him for the next 8 years. The result would be nothing less than a new understanding of how the planets move through the sky. The master of naked eye observation had provided the raw material, and now it was time for a mathematician to build something new from it. In a cramped study in Prague, sometime around 1605, Johannes Kepler stared at a page of calculations and realized he had been wrong for years. He had spent the better part of a decade trying to make the orbit of Mars fit a circular path. He had adjusted every mathematical device in the astronomer's toolkit, twisted and turned the circles in every way he could imagine, and nothing worked. Tycho Brahe's observations were simply too precise to allow a circular orbit. There was always a leftover error of about 8 arc minutes, a tiny fraction of a degree, roughly a quarter of the width of the full moon as seen in the sky. Any astronomer before Kepler would have shrugged off such a small discrepancy as a flaw in the observations themselves. But Kepler knew that Tycho's measurements were reliable to about 2 arc minutes, and 8 was 4 times that. The error was real, and it meant something profound. Mars does not move in a circle. In a moment of extraordinary intellectual courage, Kepler abandoned the assumption that had governed astronomy for 2,000 years, the belief that all heavenly motion must be built from perfect circles. He began testing other shapes. He tried ovals, egg shapes, and various curves, documenting nearly 70 failed attempts in his book before he found the answer. The orbit of Mars was an ellipse, a gently stretched circle with the sun sitting not at the center but at one of 2 special points called the foci. It was a shape that Greek mathematicians had studied in the abstract, but that no one had ever imagined tracing a path through the heavens. Johannes Kepler was born in 1571 in a small town in southwestern Germany. His early life was hard. His father was a mercenary soldier who abandoned the family when Kepler was a child. His mother was an herbalist and healer who would later be accused of witchcraft, dragging Kepler into years of legal struggle to defend her. Kepler himself was sickly all his life, troubled by fevers, stomach problems, and severe nearsightedness. A painful irony for a man who would change how we understand the sky. His poor vision meant he could never be a great observer. His gift was entirely mathematical. Despite all of these hardships, his extraordinary intelligence won him a scholarship to the University of Tübingen, where he studied under one of the few professors in Europe who openly taught the sun-centered system of Copernicus as a description of physical reality, not just a mathematical trick. That teacher's influence was decisive. Kepler became a devoted follower of Copernicus and never looked back. His first published work, written when he was just 25, tried to explain the spacing of the planetary orbits by fitting the 5 perfect solid shapes known to the Greeks between them. The idea was ingenious and entirely wrong, but it showed the world a mind passionately convinced that the universe is built on mathematical harmony. The book also brought him to the attention of Tycho Brahe, who invited Kepler to Prague in 1600 to serve as his mathematical assistant. When Tycho died the following year, Kepler moved quickly to secure the treasure trove of observational data, and he was appointed to Tycho's former position as imperial mathematician. He set to work on the orbit of Mars, and for 8 long years it consumed him. The book that resulted, published in 1609, announced 2 of the 3 great laws that bear his name. The first law said that the orbit of every planet is an ellipse, with the sun at one of its 2 foci. The second said that a planet moves faster when it is closer to the sun and slower when it is farther away in a precise and measurable way. Specifically, a line drawn from the planet to the sun sweeps out equal areas in equal amounts of time. Together, these 2 laws destroyed the ancient assumption that the heavens must move in perfect circles, and they replaced it with a new picture that was mathematically exact and beautifully confirmed by the data. What makes Kepler's book so unusual and so moving is that he did not simply announce his discoveries. He told the story of how he found them, including all of his wrong turns, his frustrations, and his false starts. He devoted an entire chapter to a circular orbit that was almost right but failed by those critical 8 arc minutes, showing the reader precisely why the old approach could not work. It is one of the most honest accounts of scientific discovery ever written, and it reveals a mind that was both rigorous and deeply romantic, driven by mathematical precision, but inspired by a belief that the universe is a work of divine art. In the same book, Kepler speculated about a force coming from the sun that sweeps the planets along their paths, using the idea of magnetism as an analogy. He was reaching toward the concept of gravity, though the mathematics to express it fully would not exist for another 70 years. Kepler's third law appeared a decade later, in 1619, in a sprawling work that combined music, geometry, and astronomy in a search for the mathematical structure of creation. The third law says that the time a planet takes to complete one orbit is related in a precise way to the size of that orbit. Specifically, if you square the period and compare it to the cube of the orbit's average distance from the Sun, the ratio is the same for every planet. Kepler described the moment of this discovery with something close to ecstasy, writing that the die was cast and his book was written, whether to be read now or in the future, for it could wait 100 years for its reader, just as God had waited thousands of years for someone to understand his work. While his astronomical discoveries secured his place in history, Kepler's personal life remained a long chain of sorrows. His first wife died of fever. 3 of his children died in infancy. His mother's witchcraft trial, which dragged on for 6 years, forced him to travel repeatedly to defend her. She was imprisoned for over a year and shown the instruments of torture before being finally released, largely thanks to her son's tireless legal work. She died 6 months later, broken by the ordeal. Kepler himself, a Protestant caught in the religious wars tearing Europe apart, was excommunicated by his own church and forced to move again and again as regions changed hands. Kepler died in 1630 in a small Bavarian city, exhausted and nearly penniless, still owed a fortune in unpaid salary by the emperor. His grave was destroyed during the wars that ravaged the region, and no one knows where it lies. But his 3 laws survive as true today as the day he found them. Every spacecraft launched into orbit, every prediction of a planet's path, every calculation of a comet's return rests on the foundations that Kepler built in his cramped study, working with Tycho's numbers and an unshakable faith that the cosmos is made of mathematics. And now the story moves to Italy, where another man, working at almost the same time as Kepler, pointed a simple tube of glass at the sky and changed what we could see forever. On a cold evening in January of 1610 in the city of Padua, a 45-year-old mathematics professor pointed a long tube fitted with glass lenses at both ends toward the bright point of Jupiter and saw something no human being had ever seen before. 3 small points of light were arranged in a line near the planet, 2 to one side and 1 to the other. Galileo Galilei assumed at first that they were ordinary background stars. But when he looked again the following night, the arrangement had changed. Over the next 2 months, watching almost every clear night, he tracked the shifting positions of what turned out to be 4 tiny moons orbiting Jupiter. The implications were enormous. If Jupiter had its own moons, then not everything in the universe orbited the Earth. The most basic assumption of the Earth-centered model was simply wrong. The instrument that made this possible was not Galileo's own invention. The telescope had appeared in the Netherlands in 1608, when a spectacle maker filed a patent for a device that made distant objects appear close. The patent was denied because the device was judged too easy for anyone to copy, and within months, word of the invention had spread across Europe. An English mathematician used an early telescope to sketch the surface of the moon several months before Galileo did, but he never published his observations. It was Galileo who grasped the telescope's revolutionary potential for astronomy and who had the skill, the training, and the instinct for publication to make the most of it. Galileo improved the Dutch design by grinding his own lenses, achieving a magnification of about 20 times, far better than the 3 or 4 times that the earliest instruments could manage. He published his first telescopic observations in March of 1610 in a short book he called The Starry Messenger, and the impact was immediate. The book described not only the moons of Jupiter, but also the surface of our own moon, which turned out to be rough and mountainous, covered in craters and valleys, nothing like the smooth, perfect sphere that the followers of Aristotle had imagined. He also turned his telescope on the Milky Way and discovered that it was made up of countless individual stars, far too faint to see with the naked eye. The universe, it seemed, was enormously richer and more complex than anyone had supposed. In the months that followed, Galileo made further discoveries that strengthened the case for the sun-centered system. He observed that Venus goes through a full set of phases, from a thin crescent to a nearly full disk, exactly as it would if it orbited the Sun. In the Earth-centered model of Ptolemy, Venus should only ever appear as a crescent, because it would always be between us and the Sun. Seeing a full Venus was proof that Ptolemy's arrangement was wrong, though it could also be explained by the compromise model that Tycho Brahe had proposed. Galileo also observed dark spots on the surface of the Sun, blemishes that moved and changed from day to day, yet more evidence against the old teaching that the heavens are perfect and unchanging. Saturn, too, offered puzzles. Through his early telescope, Galileo could see that Saturn was not a simple point of light. It seemed to have something on either side, which he described as a pair of ears or handles. He could not see clearly enough to recognize them as rings, a discovery that would have to wait for better telescopes some 45 years later. When the rings temporarily vanished from view as Saturn's angle changed, Galileo was bewildered, writing in a letter that Saturn appeared to have swallowed its own children. Even the limitations of his instrument were producing mysteries that would keep astronomers busy for decades. Galileo's passionate support for the Copernican system brought him into growing conflict with the Catholic Church. In 1616, the Church issued a formal decree declaring the sun-centered theory to be wrong and contrary to Scripture, and a powerful cardinal personally warned Galileo not to teach or defend the idea. For several years, Galileo was careful, at least in public, but in 1632, he published a masterpiece of scientific argument, written as a conversation among 3 characters. The book was supposedly balanced, presenting both the Earth-centered and the Sun-centered views, but its structure made the Copernican arguments overwhelmingly more persuasive. The character defending the old Ptolemaic system was portrayed as slow-witted and easily outmatched. The Pope, who had once been friendly to Galileo, was furious when he learned that some of his own arguments had been put into the mouth of this hapless character. Galileo was called to Rome in 1633 and put on trial before the Church's court of inquiry. The political situation was tangled and difficult, shaped by the pressures of war and rivalry among powerful church leaders, and the trial was not the simple clash of science and faith that it is sometimes made out to be. On the 22nd of June, Galileo was found guilty of being strongly suspected of holding false beliefs and was sentenced to formally deny the sun-centered theory and to spend the rest of his life under house arrest. A famous legend says that as he rose from his knees after making his denial, he muttered under his breath, "And yet it moves," though this almost certainly did not happen. Galileo spent his last 9 years confined to his home near Florence. Despite his failing eyesight and his isolation, he completed what many consider his most important work, a book on the science of motion and the strength of materials that laid the groundwork for much of modern physics. Its influence on the next great figure in our story, Isaac Newton, would be profound. Galileo went completely blind in 1638 and died in January of 1642 at the age of 77. It would take more than 300 years for the Church to formally acknowledge that Galileo had been right. In 1992, the Pope issued a statement expressing regret for the way the case had been handled. The telescope that started the revolution was a simple tube of wood and glass, but what it revealed, the moons of Jupiter, the phases of Venus, the mountains of our own moon, the uncountable stars of the Milky Way, could not be unseen. Galileo had opened a door, and through it, all of modern astronomy would eventually pass. And now, one more great mind awaited on the other side of that door, a man who would take Kepler's laws, Galileo's observations, and the stubborn puzzle of falling objects and weave them all together with a single elegant idea. In the summer of 1684, an astronomer named Edmund Halley traveled from London to Cambridge to visit Isaac Newton with a question that had been tormenting him and two of his most brilliant colleagues. If the force pulling the planets toward the sun grows weaker with the square of the distance, what shape would a planet's orbit take? The other two had debated the problem without solving it. One had even offered a prize for the answer, and no one had claimed it. When Halley put the question to Newton, the answer came at once: an ellipse. Newton said he had calculated it years ago, but had misplaced the paper. Halley was stunned. He urged Newton to redo the calculation and publish it. The result, produced over the next 2.5 years of intense, almost obsessive work, was a book that many consider the most important scientific work ever written. Isaac Newton was born on Christmas Day, 1642, in a small village in the English countryside. His father had died 3 months before his birth, and his mother remarried when he was 3, leaving him in the care of his grandmother. The childhood was lonely, and Newton grew into a man who was brilliant, secretive, and fiercely solitary. He studied at Cambridge, and during the years of the Great Plague in 1665 and 66, when the university closed and Newton retreated to his family home, he made discoveries in mathematics, optics, and the theory of gravity that would have been enough to fill several lifetimes of lesser minds. The famous story of the falling apple, though probably polished in the retelling, captures a genuine flash of insight. Newton realized that the force that pulls an apple to the ground is the very same force that holds the moon in its orbit around the Earth. The same invisible hand reaches from the ground beneath your feet to the farthest planet in the sky. The book that Halley's visit set in motion was published in 1687, and it changed everything. In its pages, Newton showed that a single mathematical law, a single equation, could explain Kepler's 3 laws of planetary motion: the rise and fall of the tides, the slow wobble of the Earth's axis that Hipparchus had discovered nearly 2,000 years earlier, the orbits of comets, and the tiny gravitational tugs that the planets exert on one another. The law itself is beautifully simple. Every piece of matter in the universe attracts every other piece of matter with a force that depends on how massive the objects are and how far apart they stand. Double the distance and the force drops to 1/4. Triple the distance and it drops to 1/9. This one idea, expressed in a single equation, described the behavior of everything from a falling leaf to the orbit of Saturn. Newton also built the first practical reflecting telescope, using a curved mirror instead of a glass lens to gather and focus light. Telescopes that used lenses suffered from a problem where different colors of light came to focus at slightly different points, producing blurry rainbow-fringed images. A mirror avoids this problem entirely, and Newton's design became one of the standard forms of telescope that astronomers use to this day. The most dramatic confirmation of Newton's theory came from Halley himself, though he did not live to see it. Using Newton's laws, Halley analyzed the paths of comets that had been observed in 1531, 1607, and 1682, and he concluded that all 3 were the same object, returning roughly every 76 years on a long, stretched-out elliptical orbit. He predicted that the comet would return between 1758 and 1759. On Christmas Day of 1758, an amateur astronomer in Germany spotted it in the sky, almost exactly where and when Halley had said it would be. It was a spectacular confirmation of both Newton's theory and Halley's prediction, and the comet has carried Halley's name ever since. Before Newton, astronomers could describe the movements of the planets with their models and their mathematical tables, but they could not explain why the planets moved as they did. After Newton, the answer was clear: gravity. The same force, following the same mathematical law everywhere and always, governed every motion in the universe. This was the birth of a new kind of astronomy, one that used the laws of physics to calculate the paths of the heavenly bodies with a precision that seemed almost miraculous. Over the next 2 centuries, mathematicians and astronomers would use Newton's framework to predict the return dates of comets, calculate the gravitational pushes and pulls that the planets exert on one another, and even discover entirely new planets by the disturbances they cause in the orbits of their neighbors. The universe that Newton revealed was sometimes described as a vast clockwork, a machine set in motion and running forever according to precise, knowable laws. A great French mathematician of the late 1700s pushed this idea to its ultimate conclusion, calculating the gravitational interactions of the planets with such precision that, when asked where God fitted into his picture of the solar system, he is said to have replied that he had no need of that particular idea. Newton himself would have been troubled by such a statement. He spent far more time on theology, ancient history, and secretive experiments with metals and minerals than he ever spent on physics, and he believed deeply in a God who had designed the universe with purpose. He died in London in 1727 at the age of 84 and was buried with the honors of a national hero. A poet composed a famous epitaph suggesting that nature's laws had lain hidden in darkness until God sent Newton to bring light. The universe Newton described was mathematical, precise, and beautiful. The gravity that held it together was as mysterious as it was powerful. Newton could describe its effects with perfect accuracy, but he freely admitted that he could not explain what gravity actually is, how one object can pull on another across empty space. That deeper question would wait 2 centuries for an answer. And so, armed with Newton's laws, astronomers set out to measure the heavens with a precision that the ancients could never have imagined. Let us follow them now into the age of great star catalogues, daring expeditions, and the painstaking work of mapping the sky. On the morning of June 3rd, 1769, a young naval officer named James Cook stood on a beach in Tahiti and watched as a tiny black dot crept slowly across the face of the sun. That dot was the planet Venus, and Cook had sailed halfway around the world for this moment. His instructions from the Royal Society in London were precise. He was to measure the exact times at which Venus entered and left the disk of the sun so that astronomers back home could combine his observations with those made from other points on the Earth and calculate, at last, the true distance from the Earth to the sun. The transit of Venus, a rare event in which Venus passes directly between us and the sun, was the great scientific expedition of the 18th century, and it sent observers to the farthest corners of the globe. The idea was elegantly simple. If you watch Venus cross the sun from 2 widely separated places on Earth, you will see it follow slightly different paths across the solar disk, just as a finger held at arm's length seems to jump position when you close one eye and then the other. By measuring that difference, and knowing how far apart the 2 observers are, you can work out the distance to Venus, and from that, the distance to the sun itself. Venus transits come in pairs, 8 years apart, with each pair separated from the next by more than a century. The pair that fell in 1761 and 1769 were the first to occur since the method had been proposed, and the scientific world mobilized on an extraordinary scale. The first transit in 1761 involved more than 100 observers from 9 countries, stationed at over 60 sites around the world. A French astronomer trekked across the frozen wastes of Siberia during winter to reach his observing point in time. The results from that first attempt were disappointing. Poor weather at many sites and an unexpected optical effect that made it difficult to time the exact moment of contact introduced large errors. The second transit, 8 years later, produced better results. Cook's expedition to Tahiti was the most famous of many. Using the combined data from both transits, astronomers calculated the distance from the Earth to the Sun at roughly 150 million kilometers. The modern value measured with spacecraft and radar is just under 150 million kilometers. With wooden ships and brass instruments, the 18th century had measured the scale of the solar system to within a few percent. But there is a sad story within this triumph that is worth knowing. A French astronomer set out for India to observe the 1761 transit, but war prevented him from landing at his destination, and he was forced to make his observations from a rocking ship, which made the data useless. Determined to catch the next transit 8 years later, he stayed in the region, waiting. On the day of the second transit, clouds rolled in and covered the sun at the critical moment. When he finally returned to Paris after 11 years away, he found that he had been declared legally dead. His wife had remarried, and his relatives had divided his belongings among themselves. It is one of the most heartbreaking stories in the history of science. The 18th century was also the golden age of the star catalogue. The first Astronomer Royal of England, working at the new Royal Observatory at Greenwich, spent decades compiling the first great telescope-era catalogue of the stars. Published after his death in 1725, it listed the positions of nearly 3,000 stars with an accuracy far better than anything before. The work set a new standard for measuring the sky, though the astronomer's life was made difficult by bitter disputes with Newton and Halley over who had the right to publish his data. The third Astronomer Royal made 2 discoveries that were worth more than any catalogue. In 1728, while trying to detect the tiny shift in star positions that would prove the Earth is moving through space, he found instead a small systematic distortion in the apparent positions of all the stars, caused by the combination of the speed of light with the Earth's orbital motion. Imagine walking through falling rain. Even if the rain falls straight down, it appears to come at you from a slight angle because of your own forward motion. Light behaves in much the same way, and the discovery of this effect provided the first direct evidence, independent of any argument about the planets, that the Earth really is moving through space. 20 years later, the same astronomer discovered a tiny wobble in the Earth's spinning axis caused by the gravitational pull of the Moon, a further refinement of the picture of our planet's motion. Meanwhile, a French astronomer devoted to the hunt for comets was making an accidental contribution that would last far longer than any comet sighting. Comets, when first spotted, look like faint fuzzy patches in the sky, and they can easily be confused with other fuzzy objects that never move at all, the nebulae and star clusters scattered across the heavens. Tired of being fooled, this astronomer began keeping a list of the permanent fuzzy objects so he could avoid them in the future. He eventually catalogued 110 of them, and he considered each one a nuisance, an obstacle in his comet hunt. But his list of nuisances became one of the most famous catalogues in astronomy. It includes some of the most beautiful objects visible through a small telescope, the Great Nebula in Orion, the nearest large galaxy in the constellation of Andromeda, the Pleiades star cluster, and the remains of the star that Chinese astronomers recorded exploding in 1054. The irony is lovely. He meant to ignore them, and instead he ensured they would be studied forever. By the end of the 1800s, astronomy had been transformed from a descriptive art into a precision science. The scale of the solar system had been measured. The positions of thousands of stars had been catalogued with unprecedented accuracy. The motion of the Earth through space had been confirmed by direct observation. The stage was set for the next great challenges, understanding what the stars actually are, how far away they truly lie, and what they are made of. And to answer those questions, astronomers would need an entirely new kind of tool, one that would let them read the very light that the stars send our way. On the night of March the 13th, 1781, a German-born musician who had become an astronomer was scanning the sky from the garden of his home in the English city of Brahe. His name was William Herschel, and he was using a telescope he had built with his own hands, a 7-foot reflecting instrument with a mirror he had ground and polished himself. As he swept through the constellation of Gemini, he noticed an object that did not look quite right. Through his telescope, it appeared not as a sharp point of light, the way a star should, but as a tiny disk. He assumed at first that it must be a comet. But, as other astronomers tracked the object over the following weeks, it became clear that it was moving too slowly and in too nearly circular a path to be a comet. It was something far more extraordinary. It was a planet, the first new planet discovered since before the beginning of recorded history. For as long as anyone could remember, the solar system had contained 6 worlds: Mercury, Venus, Earth, Mars, Jupiter, and Saturn. These were the same planets that the Babylonians had tracked, the same planets that the Greeks had named, the same planets that Ptolemy and Copernicus and Kepler had worked into their models of the sky. The idea that there might be another had simply not occurred to anyone. Herschel wanted to name his discovery after the King of England, but the name did not catch on outside Britain, and eventually the astronomical community settled on Uranus, the ancient Greek god of the sky, keeping with the tradition of naming planets after the gods of old. William Herschel was one of the most remarkable figures in the story of astronomy. He had come to England from the German city of Hanover as a young man and built a career as a professional musician, working as an organist and music teacher. His interest in astronomy was sparked by a book on optics, and he soon began building telescopes with a skill that put many professional instrument makers to shame. His sister Caroline, who had followed him to England, became his tireless assistant and eventually a distinguished astronomer in her own right. She discovered 8 comets over the course of her career and became the first woman to receive the Gold Medal of the Royal Astronomical Society, a recognition of work that had too often been done in her brother's shadow. Beyond the discovery of Uranus, Herschel reshaped our understanding of the universe in ways that are easy to overlook. He conducted vast surveys of the sky, cataloging thousands of nebulae and star clusters, and he was the first astronomer to try to determine the actual shape of the Milky Way. By counting the number of stars visible in different directions, he produced a model of our galaxy as a flattened disk, with the sun somewhere inside it. His model had limitations. He assumed that all stars give off roughly the same amount of light, which is not true, but it was the first attempt by anyone to map the structure of the galaxy from the inside. He also made a discovery that had nothing to do with visible light at all. In 1800, he was testing colored filters for solar observation when he placed a thermometer just beyond the red end of the visible spectrum, in a region where no light could be seen, and found that the temperature rose. He had discovered a kind of invisible light that we now call infrared radiation. It was the first hint that the universe radiates energy in forms our eyes cannot detect, a realization that would eventually open entirely new ways of seeing the cosmos. His largest telescope, a monster with a mirror 4 feet across and a tube 40 feet long, was completed in 1789 with a generous grant from the king. On its very first night of use, Herschel discovered a new moon orbiting Saturn. The telescope was clumsy and difficult to use, and Herschel actually made most of his important discoveries with smaller, more practical instruments. But the giant telescope proved an important principle, that bigger mirrors gather more light and reveal fainter objects, a principle that has driven telescope design from that day to this, all the way to the enormous mirrors being built in the deserts of Chile today. The discovery of the next planet, Neptune, came about in an entirely different way, and it remains one of the most celebrated triumphs of mathematical science. By the 1840s, astronomers had been tracking Uranus long enough to notice something troubling. The planet was not following the path that Newton's laws predicted. It was drifting away from its calculated position, tugged by the gravitational pull of something unseen farther out in the darkness beyond. 2 young mathematicians, working independently and unknown to each other, set out to find the hidden planet by pure calculation. One was English, working at Cambridge, and the other was French, working in Paris. Both used Newton's law of gravity. the observed drift of Uranus, and the formidable mathematics of celestial mechanics to calculate where the unknown planet must be. The Englishman finished first in 1845 and sent his results to the Astronomer Royal, who unfortunately did not act on them with the speed they deserved. The Frenchman completed his own calculation the following summer and sent his predicted position to an astronomer at the Berlin Observatory. On the night of September the 23rd, 1846, the Berlin astronomer pointed his telescope at the spot the Frenchman had indicated and found Neptune within 1 degree of the predicted position. The entire observation took less than an hour. It was one of those moments in science that feels almost like magic. A planet had been discovered not by looking through a telescope, but by solving an equation. Mathematics alone had predicted the existence and location of a world that no human eye had ever seen, and observation had confirmed the prediction with breathtaking precision. Gravity, it turned out, was not just a force that moved the planets we already knew about. It was a tool for finding planets we had never imagined. The argument over who deserved credit, the Englishman who calculated first or the Frenchman whose calculation actually led to the telescope being pointed in the right direction, was fierce and colored by national pride. Today, most historians agree that both men deserve recognition, though the Frenchman holds a slight edge because he published his work and communicated it effectively. But what matters most is not the dispute but the achievement itself. The clockwork universe of Newton had passed its greatest test. Unseen worlds could be found by the power of mathematics alone, and the sky held more wonders than the ancients had ever dreamed. Let us turn now to a different kind of discovery, one that did not involve finding new worlds in the sky, but finding out at last what the stars themselves are made of. In 1814, in a workshop in the German city of Munich, a young glassmaker named Joseph von Fraunhofer was testing a new kind of optical glass when he noticed something strange. He had passed a beam of sunlight through a glass prism to spread it into its familiar rainbow of colors, from red through orange, yellow, green, blue, and violet. But the rainbow was not smooth. It was crossed by hundreds of fine dark lines, narrow gaps where certain colors seemed to be missing. The lines were sharp and fixed in position, and Fraunhofer, with the careful eye of a craftsman, mapped nearly 600 of them, labeling the most prominent ones with letters that astronomers still use today. He had no idea what caused these lines. He could not have guessed that they were the fingerprints of chemical elements in the sun's outer atmosphere, each element absorbing light at its own particular set of colors. But by cataloging them so carefully, he opened a door that would, within half a century, allow astronomers to determine what the stars are made of without ever leaving the Earth. The explanation came in 1859, when two German scientists working at the University of Heidelberg made a discovery that changed everything. They showed that every chemical element, when heated until it glows, gives off light at a unique set of colors, producing a pattern of bright lines as distinctive as a fingerprint. And they realized that the same elements, when present as a cooler gas in front of a hotter light source, absorb light at exactly those same colors, producing dark lines instead. The dark lines in the sun's rainbow were therefore the signatures of the elements in the sun's atmosphere, each one stealing its own particular colors from the light streaming up from the hotter layers below. This single discovery demolished a claim that had been made just 24 years earlier by a famous French philosopher who had declared that the chemical makeup of the stars was a question humanity could never answer. We could never bring a piece of a star into a laboratory, he argued, so we could never know what stars are made of. And then two scientists in Heidelberg proved him wrong without leaving their workbench. The light itself carried the information, and the language of these spectral lines could be read from any distance, whether the source was a candle flame across the room or a star at the far edge of the galaxy. An English astronomer was among the first to point this new tool at the stars. Working from a private observatory in London in the 1860s, he showed that the stars contain the same elements found on Earth: hydrogen, sodium, calcium, iron. This was a revelation. For more than 2,000 years, since the time of Aristotle, educated people had believed that the heavens were made of a fundamentally different substance from the things we find on the ground. Now it turned out that the stars are made of the same stuff we are, the same atoms, the same elements arranged in different proportions and burning at temperatures we can barely imagine, but fundamentally the same. This English astronomer also figured out how to measure whether a star is moving toward us or away from us by looking at tiny shifts in the positions of its spectral lines, a technique that would become one of the most important tools in all of astronomy. In 1868, this new science produced its most dramatic moment. During a total eclipse of the sun, observed from India, a French astronomer noticed a bright yellow line in the light of the sun's outer atmosphere that did not match any element known on Earth. An English astronomer working independently saw the same line and concluded that it must belong to a new element that existed on the sun but had not yet been found on our planet. He named it after the Greek word for the sun. It was a bold claim, an element discovered 93 million miles away before anyone had found it in a laboratory on Earth. Nearly 3 decades later, a Scottish chemist isolated the same element from a mineral sample, confirming the identification. The element that had first been found on the sun was sitting quietly in the rocks beneath our feet all along. The technique for measuring the motion of stars by the shifting of their spectral lines would prove even more important than anyone at first imagined. In the 1910s, an American astronomer used this method to measure the speeds of certain fuzzy patches of light in the sky, objects that were then called spiral nebulae, and discovered that nearly all of them were rushing away from us at enormous speeds, some exceeding 1,000 kilometers per second. These measurements were the first hints that the universe itself is expanding, though their full meaning would not be understood until they were combined with distance measurements a decade or so later. A quiet observation in a small Arizona observatory had planted the seed of one of the most important discoveries in the history of science. The study of starlight also revealed that the universe is made primarily of the simplest and lightest element of all, hydrogen. The spectrum of nearly every star showed strong lines belonging to hydrogen, and as methods improved, it became clear that hydrogen is by far the most common substance in the cosmos. This observation would eventually be crucial to understanding how stars produce their energy, but in the 1800s, that answer still lay in the future. The sun was clearly pouring vast quantities of energy into space, but no known chemical or mechanical process could sustain that output for more than a few thousand years, a span that contradicted the growing geological evidence that the Earth, and therefore the sun, must be enormously old. The tool that Fraunhofer had accidentally created transformed astronomy in a way that no new telescope could. Before his dark lines were explained, astronomers could tell you where a star was in the sky and how it moved. Afterward, they could tell you what the star was made of, how hot it was, and whether it was coming toward us or moving away. The rainbow of starlight, which Newton had first spread with a prism more than a century earlier, became a kind of alphabet for the cosmos, and every wavelength of light carried a message from the source that had sent it. Learning to read that message was one of the great achievements of the 19th century, and it is a message that astronomers are still reading today, with instruments that Fraunhofer could not have dreamed of, detecting light that human eyes could never see. And now, as we move into the turn of a new century, we will meet a group of remarkable women who took this new alphabet of starlight and used it to classify the heavens, uncovering a pattern that would eventually unlock the true scale of the universe. In 1881, the director of the Harvard College Observatory was fed up with his male assistants. According to a story that may or may not be perfectly true, but captures something very real, he declared that his Scottish maid could do a better job than the men he was paying. And then he hired her. Williamina Fleming had arrived in Boston from Scotland, pregnant and abandoned by her husband, and had taken work as a servant in the director's household. Now she found herself sitting at a desk in the observatory, examining glass photographs of starlight and classifying stars by the patterns of dark and bright lines in their spectra. She would go on to discover a famous cloud of dark dust shaped like a horse's head, to classify more than 10,000 stars, and to help build the foundation of our modern understanding of what stars are. She was the first of a group of women who would quietly transform astronomy from behind their desks, in an era when they were not even allowed to use the telescopes themselves. The director's decision to hire women was driven partly by practical thinking and partly by economics. The work of sorting through stellar spectra required patience, precision, and intelligence, but it was also repetitive and time-consuming, and women could be hired at a fraction of the salary paid to men. The women who worked at Harvard earned roughly half what a male secretary would have been paid. They were called computers, a word that at the time meant a person who does calculations, not a machine. Despite the low pay and the sometimes dismissive attitudes of their male colleagues, these women produced work of lasting scientific importance. Annie Jump Cannon, who joined the Observatory in 1896, developed a way of classifying stars by their spectra that is still used around the world today. She organized stars into groups based on the temperature of their surfaces, from the hottest blue-white stars to the coolest deep red ones, and she assigned each group a letter. Over the course of her career, Cannon personally classified the spectra of more than 350,000 stars, a feat of sustained concentration and pattern recognition that has never been equaled by any single person. But it was Henrietta Swan Leavitt who made the discovery that would, more than any other, unlock the true scale of the universe. Leavitt joined the observatory as a volunteer in 1893 and was assigned the task of finding stars whose brightness changes over time in two small companion galaxies visible from the southern sky. Working with photographs taken at a Harvard station in Peru, she identified nearly 1,800 of these variable stars. And among a particular type, she noticed something remarkable. The brighter the star, the longer it took to complete one cycle of brightening and dimming. In 1912, she published her findings, showing a clear and simple relationship between the period of these pulsing stars and their true brightness. This may sound like a small thing, but think about what it means. If you know how bright a star truly is, and you can measure how bright it appears from where you stand, you can calculate how far away it must be. It is the same principle by which a candle looks dimmer when it is farther away. Leavitt had given astronomers a measuring stick for the universe, a way to determine the distances to objects far too remote for any other method to reach. This discovery would prove essential, just a few years later, to the finding that the universe is far larger than anyone had imagined. Leavitt did not live to see the full impact of her work. She died in 1921 at the age of 53. A few years after her death, a Swedish mathematician wrote to her to nominate her for a Nobel Prize, not knowing she had already passed away. The Nobel Prize cannot be given to someone who has died, and so one of the most important discoveries in the history of astronomy went unrecognized by the prize committee. Another of the Harvard computers, Antonia Mori, made an observation that was ahead of its time. She noticed that stars of the same spectral type sometimes showed differences in the fine details of their spectral lines, differences in how sharp or wide the lines appeared. She proposed a secondary way of sorting stars based on these details, but the director dismissed her refinement as unnecessary. Years later, a Danish astronomer realized that Mori's categories actually distinguished between ordinary stars and giant stars, enormously large and bright stars that look similar in their basic spectra but are fundamentally different in their nature. Her overlooked observation turned out to be a key piece of the puzzle of how stars evolve. Perhaps the most dramatic story of all belongs to a young Englishwoman named Cecilia Payne, who arrived at Harvard in 1923 to pursue a doctorate. Using new ideas from physics about how atoms behave at different temperatures, Payne analyzed the spectra of stars and reached a conclusion that was both simple and revolutionary. The enormous differences in the appearance of stellar spectra were caused not by the stars being made of different materials, but by differences in temperature. Even more remarkably, her analysis showed that stars are made overwhelmingly of hydrogen, the simplest and lightest element, with helium as the second most common, and everything else making up only a tiny fraction. This finding was correct, but it was immediately challenged by the most powerful astronomer of the day, who told her that her result was almost certainly wrong. She bowed to his authority and included a statement in her published thesis backing away from her own conclusion. A few years later, the same man independently reached the same conclusion using different methods and published it with only a brief mention of her earlier work. For decades, he received the credit. Payne eventually became the first woman to hold the rank of full professor in Harvard's Faculty of Arts and Sciences, but only after decades of being classified under less prestigious titles to avoid giving her the recognition she deserved. A later astronomer called her doctoral thesis the most brilliant ever written in the field. The story of the Harvard computers is not only a story about the contributions of women in science, though it is powerfully that. It is a story about how the most transformative discoveries can emerge from work that seems from the outside, like the most routine sort of labor, and about how the credit for those discoveries has not always gone where it belongs. The classification systems, the distance measuring tools, and the understanding of what stars are actually made of all came from women who were hired to do tedious work at low pay and who produced results that reshaped our picture of the universe. And that reshaped picture was about to be transformed once more by a quiet man with wild hair and a thought experiment about elevators and falling objects. On the morning of May the 29th, 1919, a British astronomer named Arthur Eddington stood beneath overcast skies on a small island off the west coast of Africa and waited for the clouds to break. A total eclipse of the sun was about to begin, and Eddington had traveled thousands of miles for this single moment. If a theory proposed by a German physicist named Albert Einstein was correct, the gravity of the sun should bend the paths of starlight passing near it, causing stars close to the sun's edge to appear slightly shifted from their true positions. The shift would be tiny, less than 2 seconds of arc, but it would be twice the amount predicted by the older theory of Newton, and measuring the difference would settle one of the most important questions in the history of science. The clouds parted just enough. Eddington's team took their photographs, and a second expedition in Brazil took more. When the glass plates were carefully measured and compared, the results matched Einstein's prediction and disagreed with Newton's. In November of that year, the findings were presented to a packed meeting of the Royal Society in London, and the next morning, newspapers around the world carried the story. The ideas of Newton, which had governed our understanding of gravity for more than 2 centuries, had been overturned. Einstein, who had been a moderately well-known physicist in Germany, became an overnight global celebrity, and he would remain one for the rest of his life. Einstein's theory, called general relativity, replaced the familiar picture of gravity as an invisible force pulling objects toward one another with something far stranger. In Einstein's picture, massive objects like the sun curve the very fabric of space and time around them, and other objects, including light itself, follow those curves. The Earth does not orbit the sun because the sun is pulling on it with some mysterious invisible thread. It orbits because the sun's enormous mass has bent the space around it into a gentle curve, and the Earth simply follows the most natural path through that curved space. Imagine a heavy ball placed on a stretched rubber sheet, creating a dip, and a smaller ball rolling along the curved surface. That is a rough, imperfect picture of what Einstein described with his equations, though the real mathematics is far more precise and beautiful. The theory predicted several things that could be tested by astronomers. It predicted that clocks in strong gravitational fields would run slightly slower than clocks in weaker ones. It predicted the existence of gravitational waves, ripples in the fabric of space and time caused by the motion of massive objects. And it predicted that if enough mass were packed into a small enough space, space and time would curve so severely that nothing, not even light, could escape. This last prediction described what we would eventually call a black hole. The first mathematical description of a black hole was worked out in 1916 by a German physicist who was, at the time, serving as a soldier on the Eastern Front of the First World War. He calculated that for any amount of mass, there exists a certain size below which that mass would trap light permanently. For an object with the mass of our Sun, that size would be a sphere only about 6 kilometers across. For an object with the mass of the Earth, it would be smaller than a marble. No one at the time believed such objects could actually exist in nature, and the idea remained a mathematical curiosity for decades. Einstein's theory also solved a puzzle that had been nagging astronomers for more than 50 years. The orbit of the planet Mercury does not follow a fixed path. The point where Mercury comes closest to the Sun slowly shifts over time, tracing a pattern like the petals of a flower. Newton's gravity could explain most of this shift, but it left a small leftover amount that could not be accounted for, about 43 arcseconds per century. Some astronomers had even proposed that an unseen planet orbiting between Mercury and the Sun might be causing the discrepancy, but no such planet was ever found. When Einstein applied his new equations to Mercury's orbit, the theory predicted exactly the observed leftover shift. Einstein later said that this calculation gave him such joy that his heart raced for days. Einstein himself was uncomfortable with some of the more extreme consequences of his own theory. When his equations naturally produced a universe that was expanding or contracting rather than standing still, he added an extra term to force the equations to describe a static, unchanging cosmos. He called this the cosmological constant. When observations a decade later showed that the universe really is expanding, Einstein reportedly called the cosmological constant his greatest mistake. In one of the great ironies of science, that same constant would make a dramatic comeback at the end of the 20th century, reinterpreted as a measure of a mysterious force accelerating the expansion of the universe. The theory also predicted that the gravity of a massive object could bend and focus the light of more distant objects behind it, acting like a kind of cosmic magnifying glass. This effect, called gravitational lensing, was first confirmed in 1979, when astronomers observed what appeared to be two identical images of a distant bright object, created by the gravity of a galaxy sitting between us and the source. Gravitational lensing has since become one of the most powerful tools in modern astronomy, used to study invisible matter, to magnify galaxies at the far edge of the visible universe, and to probe the distribution of mass on the largest scales. The consequences of general relativity for astronomy have only grown more important with time. The satellites that provide the precise positioning signals we use every day must account for the way gravity affects the flow of time, or they would quickly drift out of accuracy. Observations of spinning, collapsed stars in tight orbits around each other have provided exquisitely precise tests of the theory, and the detection of gravitational waves, which we will come to later in our story, confirmed perhaps the most dramatic prediction of all. Einstein's theory, born from imaginary experiments about elevators and falling objects, has become the foundation on which our entire modern understanding of the universe is built. Newton's description of gravity was not wrong. It was simply incomplete. Einstein revealed the deeper structure hidden beneath it, and in doing so, he gave astronomers an entirely new universe to explore. On the night of October 5th, 1923, an astronomer named Edwin Hubble sat in the observer's cage of the largest telescope in the world, a great instrument with a mirror 100 inches across, perched on a mountaintop above the lights of Los Angeles. He was photographing a fuzzy patch of light known as the Andromeda Nebula, one of the largest and brightest of the spiral-shaped objects scattered across the sky. When he examined the photograph the next day, he noticed what appeared to be a star that had suddenly brightened near the nebula's edge. He marked it with a letter on the glass plate, but as he compared the plate with earlier photographs, he realized this was not a star that had flared and faded. It was a star whose brightness rose and fell in a steady, regular rhythm. It was the kind of pulsing star that Henrietta Leavitt had studied. the kind whose period of brightening and dimming tells you exactly how luminous it truly is. Hubble did the calculation. Using Leavitt's law, he worked out the true brightness of the pulsing star, compared it to how bright it appeared on his photograph, and from that determined the distance. The answer was staggering. The Andromeda Nebula was roughly 900,000 light-years away, far beyond the outermost edge of the Milky Way. It was not a cloud of gas inside our galaxy at all. It was a galaxy in its own right, a vast island of billions of stars separated from our own by an immense gulf of empty space. On his photographic plate, Hubble crossed out his original marking and wrote a single word followed by an exclamation mark, and in that moment, the universe became a much, much larger place. This discovery settled a question that had divided astronomers for years. In 1922, prominent astronomers had debated the issue before an audience at the Smithsonian Institution in Washington. One argued that the Milky Way was the entire universe, and that the spiral nebulae were relatively small objects within it. The other insisted that the spiral nebulae were separate galaxies, island universes far beyond our own. The debate had ended without a clear winner because neither man had the evidence to settle the matter. Hubble's measurement of a single pulsing star in Andromeda provided that evidence. When the result was communicated to the astronomer who had argued for the smaller universe, he reportedly told a colleague, "Here is the letter that has destroyed my universe." By the end of 1924, Hubble had found more than 30 variable stars in Andromeda, a dozen of them the crucial pulsing type, and all of them confirmed the enormous distance. The Milky Way, which had seemed to be everything, was revealed as just one galaxy among what would eventually turn out to be hundreds of billions. But Hubble was not finished. Building on earlier work by an American astronomer who had measured the light from spiral nebulae and found that nearly all of them showed their spectral lines shifted toward the red end of the spectrum, meaning they were moving away from us, Hubble set out to measure both the distances and the speeds of these galaxies. By 1929, he had collected enough data to announce a remarkable pattern. The farther away a galaxy was, the faster it was receding from us. The relationship was simple and direct, a straight line on a graph, and it implied something almost beyond comprehension. The universe was expanding. Think about that for a moment. Every galaxy in every direction was rushing away from every other galaxy, like dots on the surface of a balloon being inflated. This did not mean that we were at the center of the expansion. It meant that space itself was stretching, carrying the galaxies apart the way rising bread dough carries raisins apart, each raisin moving away from every other without any single raisin being at the center. The idea of an expanding universe had actually been predicted before Hubble's observations by a Belgian priest and physicist named Georges Lemaitre, who in 1927 had worked out the expansion from Einstein's equations of general relativity and had even estimated how fast the universe was growing. But Lemaitre had published his paper in a small Belgian journal that few people read, and it was Hubble's observational confirmation that convinced the scientific community. The expanding universe pointed backward to a beginning. If the galaxies were flying apart now, then they must have been closer together in the past, and if you rewound the clock far enough, all the matter and energy in the universe would have been squeezed together in an unimaginably hot, dense state. Lemaitre called this the primeval atom, and the idea would eventually grow into what we now call the Big Bang theory. But in the 1930s, the concept was still controversial. Many physicists, including Einstein himself, were reluctant to accept it. Hubble spent the rest of his career at Mount Wilson, systematically cataloging galaxies and refining his measurements. He developed a way of sorting galaxies by their shapes, dividing them into groups based on whether they were rounded, spiral, or barred with a line of stars through their center. His early estimate of the distance to Andromeda turned out to be too small. The true distance, refined through decades of better measurements, is about 2.5 million light-years. But the essential conclusion was right, and it changed everything. Hubble never received a Nobel Prize, partly because there was no Nobel category for astronomy during his lifetime, and he spent years arguing that astronomical discoveries should be eligible for the Physics Prize. He died in 1953, at the age of 63. But his legacy would be honored in a way he could not have foreseen. In 1990, a space telescope carrying his name was launched into orbit, and it would carry his program of discovery far beyond anything he could have imagined, photographing galaxies so distant that their light had been traveling for billions of years before it reached the mirror. The discovery that the universe contains billions of galaxies, each containing billions of stars, all rushing apart in an expansion that has been going on for billions of years, is perhaps the most humbling finding in the history of science. In a few short decades, the human picture of the cosmos expanded from a single galaxy to an observable universe roughly 93 billion light-years across. And it all began with one pulsing star on a glass photographic plate and a man who knew what to do with the numbers. Now, there is something else worth knowing. If the universe is made of billions of galaxies and each galaxy is made of billions of stars, what are the stars themselves? How do they shine? How long do they last? And what happens when they die? Let us find out. In 1920, a British astronomer named Arthur Eddington proposed an idea that seemed almost outrageous. He suggested that stars, including our own sun, generate their energy by converting tiny amounts of matter into enormous amounts of energy, following a relationship described by Einstein's famous equation linking energy and mass. The question of what powers the sun had been one of the great puzzles of the previous century. If the sun were burning like a coal fire, it would have run out of fuel in just a few thousand years. If it were slowly shrinking, squeezing itself under its own gravity and releasing heat in the process, it could last perhaps 20 million years. But the rocks beneath our feet told a different story. The Earth, and therefore the sun, had to be billions of years old. Only processes happening deep inside the atom could produce enough energy to keep the sun shining for that long, and Eddington, with characteristic boldness, said so. The details came almost 2 decades later in 1939, when a physicist worked out the specific steps by which the sun turns hydrogen, the lightest and simplest element, into helium, the next lightest. The process happens deep in the sun's core, where the temperature is roughly 15 million degrees and the pressure is crushing. Under those conditions, hydrogen atoms are squeezed together so tightly that they fuse, combining to form helium atoms that weigh very slightly less than the hydrogen atoms that went into them. That tiny missing bit of mass is converted into energy, and it is the source of all the light and warmth the sun pours into space. The sun converts roughly 620 million tons of hydrogen into helium every second, and the small fraction of that mass that is transformed into energy is enough to illuminate an entire solar system. The process has been running for about 4.5 billion years and will continue for roughly another 5 billion. What happens to a star over the course of its life depends almost entirely on one thing: how massive it is. This insight emerged from a diagram developed independently by a Danish astronomer and an American astronomer in the early 20th century. When you plot stars on a chart with their surface temperature on one side and their brightness on the other, something striking appears. Most stars fall along a broad, diagonal band running from hot, brilliant blue stars at one corner to cool, dim red stars at the other. This band is called the main sequence, and a star's position on it is determined by its mass. Heavy stars are hot and bright. Light stars are cool and dim. The sun, a middleweight star, sits comfortably in the middle. When a star like the sun uses up the hydrogen fuel in its core, it does not simply go dark. Instead, something dramatic begins. The core, now made mostly of helium, contracts and heats up, while the outer layers of the star swell enormously, turning the star into a red giant, a cool but vast sphere that can extend outward to many times the star's original size. Deep inside, the temperatures and pressures climb high enough for helium to begin fusing into heavier elements, carbon and oxygen. Eventually, the star sheds its outer layers gently into space, forming a beautiful, glowing shell of gas, and the core that remains settles into a quiet retirement as a white dwarf, an object roughly the size of the Earth, but with the mass of a star, so dense that a teaspoonful of its material would weigh several tons. In 1930, a young Indian physicist named Subramanian Chandrasekhar, just 20 years old and traveling by ship from India to England to begin his graduate studies, made a calculation during the voyage that would change our understanding of how stars die. He showed that a white dwarf could not be stable if its mass exceeded about 1.4 times the mass of the Sun. Beyond that limit, the internal forces that hold the white dwarf up would be overwhelmed by gravity, and the star would collapse further. The calculation was brilliant, and its implications were unsettling. It meant that massive stars could not simply cool down and fade away. Something more violent had to happen. Chandrasekhar's result was initially rejected by one of the most famous astronomers of the day, who publicly dismissed it and could not accept the idea of a star collapsing beyond the white dwarf stage. The young physicist, discouraged by this opposition, eventually moved to the United States, where he continued his work for decades. He was finally vindicated when he received the Nobel Prize in Physics in 1983. More than 50 years after his shipboard calculation. Stars more massive than the limit Chandrasekhar had calculated end their lives in a far more spectacular way. When such a star runs through its nuclear fuel, its core collapses in a fraction of a second, and the outer layers are blown outward in a colossal explosion called a supernova, an event so bright that for a few weeks a single dying star can outshine the entire galaxy around it. What is left behind depends on the mass of the collapsing core. If it is not too large, the collapse is halted by the crushing pressure of particles packed unimaginably tight, forming a neutron star, an object barely 20 kilometers across, but heavier than the Sun. If the core is larger still, even this last barrier fails and the collapse continues without end, forming a black hole, a region where gravity is so strong that nothing, not even light, can escape. A British astronomer named Fred Hoyle made one of the most remarkable contributions to understanding what happens inside these stars. He predicted that a very specific property must exist in the nucleus of the carbon atom, a kind of energy level that would make it possible for 3 helium atoms to combine and form carbon deep inside a dying star. Without this property, the process of building carbon would be so unlikely that the universe would contain almost none of it, and there would be no carbon-based life of any kind. Hoyle reasoned backward from the existence of carbon to the prediction that this energy level must be there, and he persuaded experimentalists to look for it. They found it almost exactly where he said it would be. It is one of the most beautiful examples of scientific prediction in all of physics. In 1957, a landmark paper by 4 scientists laid out the comprehensive theory of how stars build the elements. They showed that virtually all the elements heavier than hydrogen and helium are forged inside stars, either during their long lifetimes or in the violent moments of their deaths. The carbon in your body was made in the core of a star that died long before the Sun was born. The iron in your blood was created in the final seconds of a massive star's life. The gold in a ring was probably made when 2 neutron stars spiraled together and collided billions of years ago. We are, quite literally, made from the remains of stars that lived and died before us. This is not poetry. It is a precise statement of physics confirmed by decades of observation. And so the stars are not eternal. They are born from clouds of gas, they burn for millions or billions of years, and they die, scattering the elements they have created back into space, where those elements become the raw material for new stars, new planets, and eventually, in at least one case that we know of, new life. Let us move on now to another great discovery, one that revealed the very beginning of everything. In the spring of 1964, Two young radio engineers at a laboratory in New Jersey were trying to get rid of a stubborn hiss in their antenna. Arno Penzias and Robert Wilson had been assigned to use a large horn-shaped instrument originally built for satellite communication experiments to do radio astronomy. But no matter what they tried, they could not eliminate a faint, steady signal that seemed to come from every direction in the sky. They cleaned pigeon droppings from the inside of the antenna. They checked every cable and connection. They pointed the antenna toward the city to see if the noise was coming from there. Nothing helped. The hiss was constant, uniform, and present at all hours of the day and night, coming from everywhere and nowhere at once. What Penzias and Wilson had stumbled upon almost entirely by accident was the echo of the beginning of the universe. That faint, uniform glow filling every corner of the sky was the remnant heat from a time roughly 380,000 years after the birth of the cosmos, when the universe had cooled down just enough for atoms to form and for light to travel freely for the first time. That light had been traveling through space for nearly 14 billion years, its waves stretched by the expansion of the universe from visible light into the much longer waves of the microwave range. And it had arrived at a horn-shaped antenna in a New Jersey field as a barely detectable whisper. It was the oldest light in the universe, and two engineers who were trying to make it go away had found it. The existence of this background glow had actually been predicted nearly 2 decades earlier. In the late 1940s, a group of physicists working on the theory that the universe began in an extremely hot, dense state had calculated that the leftover heat from that early fireball should still be detectable today, cooled down to a temperature of about 5 degrees above absolute zero. Their prediction was remarkably close to what Penzias and Wilson measured, but by the time of the actual discovery, the prediction had been largely forgotten. Neither Penzias nor Wilson knew about it when they first detected the signal. They were not looking for the beginning of the universe. They were trying to fix a noisy antenna. The connection was made by a group of scientists at Princeton University, just 40 miles away, who had independently predicted the existence of this background radiation and were in the process of building their own instrument to detect it. When they heard about the Bell Lab's measurement, they immediately understood what it was. 2 papers were published at the same time, one by Penzias and Wilson simply describing the observation, and the other by the Princeton group explaining what it meant. Penzias and Wilson received the Nobel Prize in Physics in 1978 for their accidental discovery, though the theorists who had predicted the radiation did not share the award. The idea that the universe had a beginning had a long and contentious history before this quiet hiss settled the debate. The concept traces back to a Belgian priest and physicist named Georges Lemaitre, who in 1927 had worked out from Einstein's equations that the universe should be expanding, and who proposed that if you ran the expansion backward in time, all the matter and energy in the cosmos would converge into an incredibly dense, hot state that he called the primeval atom. Einstein himself was initially skeptical, reportedly telling Lemaitre that his physics was correct, but his conclusion was unacceptable. The phrase Big Bang was actually coined in 1949 by a British astronomer who did not believe in the theory at all. He used the term on a radio broadcast to mock the idea, preferring his own theory that the universe was eternal and unchanging, with new matter continuously appearing to fill the gaps as the universe expanded. The name stuck, even though it was meant as an insult. The discovery of the background radiation was the decisive blow against this rival theory. The Big Bang naturally explained a uniform glow of leftover heat filling the entire sky. The competing theory had no way to produce such a signal. In the decades that followed, ever more precise measurements of this cosmic background revealed something remarkable. It was the most perfect example of a particular kind of light emission ever observed, matching the theoretical predictions with extraordinary accuracy. And within that near-perfect uniformity, incredibly tiny variations in temperature were found, differences of about 1 part in 100,000, representing slightly denser and slightly less dense regions in the infant universe. These tiny ripples were the seeds from which everything in the cosmos would grow, the first faint whispers of the galaxies, the stars, and the planets that would form over the billions of years to come. Satellites launched in 1989, 2001, and 2009 each produced more detailed maps of these tiny variations. And from those maps, scientists extracted a wealth of information about the universe. The age of the cosmos was pinned down to roughly 13.8 billion years. Its composition was measured with startling precision, roughly 5% ordinary matter, the kind that makes up stars and planets and people, about 27% a mysterious invisible substance called dark matter, and about 68% an even more mysterious force called dark energy, which is driving the expansion of the universe to accelerate. The shape of the universe was found to be flat, like a vast, level plane stretching out in every direction, within the limits of what could be measured. All of this information was encoded in a faint hiss that two engineers in New Jersey had tried to make go away. The cosmic microwave background, as it came to be called, turned out to be the most informative signal ever detected, a snapshot of the infant universe containing, within its subtle patterns, the blueprint for everything that would follow. It is, in a very real sense, the baby picture of the cosmos, and we can still see it every night, in every direction, if only we have the right instruments to look. And as astronomers learned to see the universe in this new light, they also discovered that visible light itself is only a tiny fraction of what the cosmos has to offer. Let us turn now to the story of invisible light and the violent, surprising universe it revealed. In 1932, a young engineer named Carl Jansky was working at a telephone laboratory in New Jersey, trying to track down the sources of static that interfered with transatlantic radio calls. He had built a rotating antenna in a field, and with it he identified three kinds of interference. Two came from thunderstorms, both nearby and distant, but the third was a faint, steady hiss that rose and fell on a cycle of 23 hours and 56 minutes. That period was not quite a normal day. It was a sidereal day, the time it takes the Earth to make one full turn relative to the stars rather than the sun, and it meant that the hiss was coming not from anything on Earth but from the sky itself. Specifically, it was coming from the direction of the center of our own galaxy, the Milky Way. Without intending to, Jansky had opened an entirely new window on the universe, one that did not rely on the kind of light our eyes can see. He had founded the science of radio astronomy. His employers showed little interest in pursuing the discovery, and Jansky himself moved on to other work. The next chapter of the story belongs to a man named Grote Reber, a radio engineer from a small town in Illinois, who built the world's first purpose-built radio telescope in his backyard in 1937. It was a dish about 9 meters across, and for nearly a decade, Reber was the only radio astronomer on the planet, working alone and at his own expense. He confirmed Jansky's discovery, mapped the radio emissions of the Milky Way, and published his results in scientific journals. Professional astronomers largely ignored him. His vindication came after the Second World War, when the technology that had been developed for radar during the conflict produced a whole generation of engineers who were skilled with radio equipment and eager to turn it toward the sky. Radio astronomy exploded in the years that followed, and the lonely backyard dish was remembered as the founding instrument of a revolution. The new radio telescopes revealed a universe that was entirely invisible to ordinary telescopes. In 1963, an astronomer studying the light from a peculiar radio source found that its spectral lines were shifted by an enormous amount toward the red end of the spectrum. If this shift was caused by the expansion of the universe, the object was billions of light years away and was pouring out energy at a rate that dwarfed entire galaxies. These objects came to be called quasars, and they were eventually understood as the brilliant cores of distant galaxies, powered by matter falling into supermassive black holes at their centers. A black hole, consuming the gas and dust around it, could produce more light than 1 trillion suns from a region no larger than our solar system. In 1967, a 24-year-old graduate student at Cambridge noticed something odd on the paper charts coming from the radio telescope she had helped to build. A small stretch of regular pulses appeared, repeating with a period of about 1 1/3 seconds, so steady and precise that she and her supervisor half-jokingly labeled the signal "little green men," wondering if it might be an artificial message from another civilization. Further searching revealed more of these pulsing sources in different parts of the sky, ruling out an alien origin. They were identified as rapidly spinning neutron stars, the collapsed remnants of massive stars, spinning many times per second and sending beams of radio waves sweeping across space like a lighthouse. The young woman who found the signal, Jocelyn Bell Burnell, was not included when the Nobel Prize was awarded for the discovery, a decision that has been widely criticized. Decades later, she received a major prize of her own and donated the entire sum to a fund for students from underrepresented backgrounds. The universe that radio telescopes revealed was far more violent and dramatic than the calm, stately cosmos visible to the naked eye. But radio waves were only the beginning. Other forms of invisible light opened still more windows. The Earth's atmosphere blocks most kinds of light from reaching the ground. Only visible light and certain radio waves make it through. To see the universe in other wavelengths, you need to get above the atmosphere, which means sending instruments into space. In 1962, a brief rocket flight detected the first source of cosmic X-rays, high-energy light produced by matter heated to millions of degrees. A satellite launched in 1970 conducted the first complete survey of the X-ray sky and revealed a violent universe of neutron stars locked in tight orbits with companion stars, gas falling toward black holes, and vast clouds of superheated material in the spaces between galaxies. The scientist who pioneered X-ray astronomy received the Nobel Prize in 2002. Infrared light, the kind William Herschel had accidentally discovered back in 1800, allowed astronomers to see through the vast clouds of dust that block visible light. Star-forming regions, hidden behind curtains of interstellar dust, became visible for the first time. Ultraviolet light revealed the hottest, youngest stars in galaxies. And gamma rays, the most energetic form of light in the universe, revealed the existence of gamma ray bursts, explosions so powerful that a single burst can release more energy in a few seconds than the sun will produce in its entire lifetime. These bursts appear to come from the most extreme events in the cosmos, the collapse of massive stars and the collision of neutron stars, and for a brief moment they outshine everything else in the observable universe. The modern practice of observing the same object across many different kinds of light, from radio waves through infrared, visible, ultraviolet, X-ray, and gamma ray, has transformed our understanding of virtually everything in the sky. A galaxy that looks peaceful and serene in visible light might reveal jets of energetic particles in radio, clouds of hot gas in X-ray, and hidden star-forming regions in infrared. Each kind of light tells a different part of the story, and the full picture only emerges when you put them all together. The universe visible to the naked eye is a tiny fraction of what is really out there. Carl Jansky's faint hiss from the Milky Way, picked up in a New Jersey field more than 90 years ago, was the first sound from a cosmos that turned out to be far noisier, far more violent, and far more surprising than anyone had imagined. And to hear even more of that cosmic music, astronomers would need to leave the ground entirely. On the evening of October 4th, 1957, a small polished metal sphere the size of a beach ball rose into the darkening sky above the flat grasslands of Central Asia, carried aloft by a converted military rocket. It weighed less than 200 pounds and measured just 23 inches across. It carried nothing more than a simple radio transmitter that sent out a rhythmic beep over and over as it circled the Earth once every 96 minutes. But that beep, picked up by amateur radio enthusiasts and tracking stations around the world, announced the beginning of something entirely new. For the first time in all of human history, an object made by human hands was orbiting the Earth, visible on a clear night as a tiny moving point of light. The space age had begun. The reaction in the United States was a complicated mix of wonder, alarm, and bruised pride. The Soviet Union, still recovering from the devastation of the war, had beaten the world's wealthiest and most technologically advanced nation into space. Congressional hearings were called within weeks. A new agency dedicated to civilian space exploration was created the following year, and the competition between the two great powers for dominance in space was underway. The early years of the space age unfolded at breathtaking speed. Just a month after the first satellite, the Soviets launched a second one, this time carrying a dog named Laika, making her the first living creature to orbit the Earth. She did not survive the flight, as there was no way to bring her back, but her mission showed that a living body could endure the conditions of space. 3 months later, the United States launched its own first satellite, and the instrument it carried made a genuine scientific discovery on its very first mission, detecting 2 vast belts of intense radiation trapped by the Earth's magnetic field. The very first American satellite had proved that space exploration and scientific research were natural partners. The competition escalated rapidly. In April of 1961, a 27-year-old Soviet pilot became the first human being to travel into space, completing a single orbit of the Earth in a capsule no larger than the interior of a small car. He became an instant global celebrity. The United States followed with its own human spaceflights, and then, in May of that year, the American president made a declaration that would define the decade. Before a joint session of Congress, he announced that the nation should commit itself to landing a person on the moon and returning them safely to Earth before the 1960s were over. The program that followed was the largest peacetime engineering project in human history, employing roughly 400,000 people. The rocket designed to carry the astronauts to the moon stood more than 360 feet tall and produced more than 7 million pounds of thrust at liftoff, enough to shake the ground for miles around the launch pad. The program suffered a devastating tragedy in January of 1967, when a fire during a ground test killed 3 astronauts inside their capsule, leading to fundamental changes in the design of the spacecraft. On July the 20th, 1969, 2 human beings stepped onto the surface of the moon for the first time. The final descent had been harrowing. The landing computer overloaded with alarms, and the commander had to take manual control to steer the craft past a field of boulders to find a safe place to set down. An estimated 600 million people, roughly 1/5 of the world's population, watched on television as the first footprint was pressed into the lunar dust. 2 astronauts spent about 2.5 hours outside the spacecraft, collecting rocks, setting up scientific instruments, and photographing the landscape, while a third orbited above in the command module. The moon landings were not just feats of engineering and political will. They were, from the perspective of astronomy, the first direct human exploration of another world. Over 6 successful landings between 1969 and 1972, astronauts brought back over 800 pounds of lunar rock and soil. The analysis of those samples transformed our understanding of the moon and of the early history of our solar system. The rocks showed that the moon was formed roughly 4.5 billion years ago, most likely from the debris left after a body about the size of Mars crashed into the young Earth. They showed that the moon's surface had been battered by intense bombardment in the first billion years of the solar system, and they gave scientists a window into a period of time for which almost no evidence survives on Earth, whose own surface has been reshaped by wind, water, and the movement of its crust. Beyond the moon, the space age sent robotic explorers to every planet in the solar system. Spacecraft flew past Venus, Mars, and Mercury in the 1960s and 70s, returning the first close-up photographs of these worlds. The first images of the surface of Mars, taken in 1965, revealed a cratered, barren landscape that dashed earlier hopes of finding signs of life. Landers touched down on Mars in 1976 and performed the first experiments designed to search for living organisms on another planet. The results were ambiguous and have been debated ever since. 2 spacecraft launched in 1977, took advantage of a rare alignment of the outer planets to visit Jupiter, Saturn, Uranus, and Neptune in a grand tour that revealed the astonishing complexity of these distant worlds, their rings, their moons, their storms. Both spacecraft are still transmitting data from beyond the edges of the solar system, more than 47 years after their launch, making them the most distant objects ever created by human hands. The Soviet Union achieved its own remarkable triumphs in planetary exploration. Soviet spacecraft became the first to land on another planet, transmitting data from the scorching surface of Venus, where temperatures reach hundreds of degrees and the atmospheric pressure is crushing. Soviet landers returned the first photographs from the surface of another world, showing a rocky, barren landscape lit by an eerie filtered light. The space age transformed astronomy from a science that could only observe the universe through a narrow window of atmosphere into one that could place instruments anywhere, in orbit around the Earth, on the surfaces of other worlds, or sailing through the vast spaces between the planets. The blanket of air above us, which makes life possible, also blocks most kinds of light from reaching the ground. By getting above it, astronomers could see the universe in ways that had never before been possible. And the most powerful eye that was ever lifted above the atmosphere was a telescope named after the man who first showed us how large the universe really is. On the morning of June the 27th, 1990, the crew of the Space Shuttle Discovery released a telescope from the shuttle's cargo bay into orbit, 340 miles above the Earth. It was a moment decades in the making. The idea of placing a large telescope above the atmosphere had been championed since the 1940s by scientists, who argued that a telescope in space would be free from the blurring caused by the swirling air above our heads and could observe kinds of light that the atmosphere blocks entirely. The project had survived budget cuts, technical delays, and a terrible accident that grounded the shuttle fleet for nearly 3 years. Now, at last, the most ambitious scientific instrument ever built was floating in orbit, its mirror 2.5 meters across, ready to deliver the sharpest images of the sky ever taken. And then the pictures came back, and something was very wrong. The images were blurry. Stars, which should have been sharp pinpoints of light, were surrounded by fuzzy halos. Engineers quickly figured out the problem. The main mirror had been ground to the wrong shape. The error was almost unbelievably small, about 1/50th the width of a human hair across the outer edge, but it was enough to ruin the telescope's vision. The most expensive scientific instrument in history, launched to worldwide fanfare, could not focus properly. The telescope became a joke, a symbol of everything that could go wrong with a big government project. But what happened next was one of the most remarkable rescues in the history of science. Engineers designed a set of corrective mirrors, small optical elements that would counteract the flaw in the main mirror, working exactly like a pair of glasses for a nearsighted eye. In December of 1993, a crew of 7 astronauts flew to the telescope aboard the shuttle and spent 11 days performing 5 spacewalks to install the corrective optics, replace instruments, and swap out the solar panels. When the first corrected images were released a few weeks later, the difference was stunning. Stars snapped into focus. Galaxies revealed spiral arms and lanes of dust in exquisite detail. The telescope was not just fixed, it was delivering on its original promise. Over the following 3 decades, this telescope became arguably the most productive scientific instrument in history. It was visited and upgraded by shuttle crews 5 times, each mission installing new cameras and instruments that kept it at the cutting edge. Its contributions to astronomy are almost too numerous to list. It measured the rate at which the universe is expanding with unprecedented precision. It took the first direct images of the dusty disks around young stars where planets are forming. It analyzed the atmospheres of planets orbiting distant stars, detecting the chemical signatures of water and other molecules. And it produced some of the most iconic images in the history of science. Among those images, one stands out as perhaps the most important photograph ever taken. In December of 1995, the telescope's director made a bold decision. He would point the telescope at a tiny, apparently empty patch of sky near the Big Dipper and leave the shutter open for 10 consecutive days. Many astronomers thought this was a waste of valuable time. What could you possibly see in a patch of sky with nothing in it? The answer, when the exposure was processed, was roughly 3,000 galaxies. Some were familiar spirals and rounded shapes relatively nearby. Others were faint, irregular smudges, the light from galaxies so distant that it had been traveling for more than 10 billion years before reaching the mirror. This single image, covering an area of sky no larger than a grain of sand held at arm's length, proved that galaxies exist in staggering numbers at enormous distances, stretching back to the earliest periods of cosmic history. It was described as a core sample of the universe, and it transformed our understanding of how galaxies form and change over time. The Space Telescope was not alone in its work above the atmosphere. Other space observatories viewed the universe in kinds of light invisible to the eye. One mapped the sky in X-rays, the high-energy light produced by matter heated to millions of degrees, revealing the hot gas in galaxy clusters, the jets streaming from black holes, and the glowing remnants of exploded stars. Another observed in infrared, the kind of light that can pass through dust clouds, revealing hidden star-forming regions and some of the most distant objects in the cosmos. A third mapped the sky in gamma rays, detecting the most violent explosions the universe has to offer. The most powerful chapter in the story of space telescopes began on Christmas Day of 2021, when a new telescope far larger and more capable than anything that had come before launched from a site near the equator aboard a European rocket. Its main mirror, over 6 meters across and made of 18 hexagonal segments coated in gold, was too large to fit inside any rocket. So it was designed to fold up like a piece of origami for the journey and then unfold itself in space. The deployment involved hundreds of steps, any one of which could have ended the mission in failure. Over the course of 2 weeks, the telescope unfolded its enormous sunshield, opened its mirror, and traveled to a point about 1.5 million kilometers from Earth, 4 times farther away than the Moon. When the first images from this new telescope were released in the summer of 2022, they caused a sensation around the world. Its deep-field image, taken in infrared light, revealed thousands of galaxies in a patch of sky that had looked empty to ground-based telescopes. Some of these galaxies were among the most distant ever observed, their light having traveled for more than 13 billion years. The telescope was seeing the universe as it looked when the very first galaxies were just beginning to take shape, less than 300 million years after the Big Bang. In its first years of operation, it has detected galaxies from the earliest ages of cosmic history, studied the atmospheres of planets around other stars, and peered into the hearts of stellar nurseries with a clarity that has surprised even the scientists who built it. There is a lovely connection between the two great space telescopes. The techniques that engineers developed to correct the flawed mirror of the older telescope were later adapted to align the 18 segments of the new one. In a sense, the older telescope's greatest failure, its blurry mirror, contributed directly to its successor's greatest success. It is a reminder that in science, the most valuable lessons often come from the things that go wrong. The story of space telescopes, from a scientist's proposal in the 1940s to a golden mirror peering at the dawn of cosmic time, is a story of human persistence and the refusal to accept that the universe should remain hidden behind a curtain of air. And as these telescopes look ever deeper into the cosmos, they have revealed mysteries that even the scientists who built them did not expect. Mysteries involving invisible matter and a strange force pushing the universe apart. In 1933, a Swiss astronomer with a famously difficult personality was studying a dense swarm of galaxies known as the Coma Cluster, a gathering of over 1,000 galaxies roughly 320 million light-years from Earth. Fritz Zwicky measured how fast the individual galaxies within the cluster were moving by analyzing the shifts in their light, and he found something deeply puzzling. The galaxies were moving far too fast. Based on the total visible mass of the cluster, all the combined light of all the galaxies he could see, there simply was not enough gravitational pull to hold the cluster together. The galaxies should have been flying apart, scattering into the darkness like sparks from a dying fire. Yet the Coma cluster had clearly held itself together for billions of years. Zwicky calculated that the cluster must contain roughly 400 times more mass than was visible, and he called the unseen substance dark matter. It was a bold conclusion, and the astronomical community largely ignored it for nearly 4 decades. The deeper problem was not merely that Zwicky could be difficult to work with, though he certainly was. It was that the idea itself seemed too outrageous. Physicists were not ready to accept that the vast majority of the matter in the universe was invisible to every instrument they possessed. It would take another scientist, working decades later with a very different temperament, to force the world to take the idea seriously. Vera Rubin grew up in Washington and fell in love with the stars as a child, watching their slow turning from her bedroom window. She faced barriers at every stage of her career. When she applied to graduate school at Princeton, she was told that women were not admitted to the astronomy program. She earned her doctorate at Georgetown University instead and began a long and fruitful collaboration with an instrument maker named Kent Ford. Together, in the late 1960s and throughout the 1970s, they set out to measure how stars orbit within spiral galaxies. The expectation, based on Newton's laws, was straightforward. In our own solar system, planets close to the Sun orbit quickly, and planets far from the Sun orbit slowly because most of the mass is concentrated at the center. The same pattern should hold for a galaxy. Stars near the bright, dense center should orbit faster than stars in the sparse outer edges. The speed should rise steeply near the center and then drop off with distance following a predictable curve. What Rubin and Ford found, beginning with their study of the Andromeda Galaxy and expanding to dozens of others, was that the speed did not drop off at all. It stayed flat. Stars in the far outer reaches of galaxies were orbiting just as fast as stars much closer to the center. This could only mean one of 2 things. Either Newton's laws of gravity were wrong at the enormous scale of galaxies, or there was a vast amount of unseen mass in every galaxy, extending far beyond the visible disk of stars into an enormous invisible halo that no telescope could see. Rubin concluded, with growing confidence and mounting evidence, that every galaxy she measured was embedded in a cloud of dark matter 5 to 10 times more massive than the visible stars and gas. By 1980, she had collected evidence from more than 60 galaxies, and the pattern was universal. Every spiral galaxy showed the same flat rotation curve, the same puzzling mismatch between what you could see and what the gravity demanded. The results could not be brushed aside as a quirk of one unusual galaxy. Something was holding these galaxies together, and it was not anything that gave off light. The combined weight of Rubin's galaxy measurements, Zwicky's earlier cluster observations, and studies by other researchers gradually convinced the scientific community that dark matter was real. By the 1980s, a picture was forming. The universe contained far more matter than could be seen, and this invisible substance dominated the gravitational behavior of everything on the largest scales. Today, the best estimates say that dark matter makes up about 27% of the total content of the universe, compared to just 5% for ordinary matter, the atoms that make up stars, planets, and our own bodies. But what is dark matter actually made of? This is one of the deepest unsolved questions in all of science. For decades, the leading idea was that dark matter consists of a type of subatomic particle that interacts with ordinary matter only through gravity, something so ghostly that it passes through everything without leaving a trace. Experiments have been built deep underground in mines and tunnels, shielded from the constant rain of particles from space, using tanks of special liquids designed to register the faintest possible interaction. Despite years of searching, nothing has been found. Other ideas have been proposed, including extremely light particles of a different kind, or even the possibility that our understanding of gravity itself needs to be revised. None of these alternatives has yet provided a complete answer. Some of the most dramatic evidence for dark matter comes from gravitational lensing, the bending of light from distant galaxies by the gravity of massive objects in the foreground. By measuring how much the light is bent, astronomers can map the distribution of mass, including mass that is invisible. One particularly striking observation involved two galaxy clusters that had crashed through each other in a cosmic collision. The hot gas from the two clusters, which interacts and slows down, was found in one place, but the bulk of the mass, mapped through its lensing effect, was found in two separate clumps that had passed through each other without interacting at all. This is exactly what you would expect if dark matter particles barely notice each other, interacting only through gravity. It is very difficult to explain this observation without dark matter. Vera Rubin never received the Nobel Prize, despite the profound importance of her work. She died on Christmas Day of 2016 at the age of 88. Many in the astronomical community considered the omission a significant injustice, but her name lives on. A great observatory now under construction in Chile, designed to map the distribution of dark matter across the cosmos with unprecedented detail, bears her name. In a fitting tribute, the telescope that carries her legacy will study the very phenomenon she spent her career revealing, a universe dominated by something we cannot see, cannot touch, and do not yet understand. And dark matter is not the only mystery. Let us turn now to an even stranger discovery, one that showed the universe is not just full of invisible matter, but is also being pushed apart by an invisible force. In January of 1998, a scientist named Saul Perlmutter stood before a room full of astronomers and presented results that he himself found hard to believe. For nearly a decade, his team had been carefully measuring a particular kind of exploding star in distant galaxies, trying to figure out how the expansion of the universe was changing over time. The expectation was simple. Gravity should be gradually slowing the expansion down, pulling the galaxies back toward each other. The only real question was how quickly the breaking was happening, whether the universe would eventually stop expanding and collapse, or continue expanding forever but at an ever slower pace. What Perlmutter's team found was neither of these things. The expansion of the universe was not slowing down at all. It was speeding up. The method they used relied on a particular type of stellar explosion that happens when a certain kind of dead star accumulates too much material from a nearby companion and detonates in a colossal blast. These explosions are special because they all happen at roughly the same mass, which means they all reach roughly the same peak brightness. If you know how bright something truly is, and you measure how bright it appears from where you stand, you can calculate how far away it must be. By measuring both the distance and the speed at which distant galaxies are receding, these exploding stars allowed the team to reconstruct the history of the universe's expansion. Perlmutter was not the only one looking. A rival team working independently on the other side of the world was doing the same kind of study. When the lead analyst of this second team finished processing his data, he realized what it was telling him. The distant explosions were slightly fainter than they should have been, meaning they were farther away than expected. The only way to explain this was if the expansion of the universe had been accelerating for billions of years, driven by some unknown force operating on the largest scales, pushing everything apart faster and faster. Both teams announced their results in 1998, and both reached the same conclusion. The fact that two completely independent groups, using different telescopes, different methods, and different sets of exploding stars, had arrived at the same answer gave the finding enormous weight. Even scientists who were deeply skeptical found it hard to dismiss. The discovery demanded an explanation, and the most natural one turned out to be something Einstein had introduced into his equations of gravity in 1917 and then thrown away. Back then, Einstein had added an extra term to his equations to prevent them from predicting an expanding or contracting universe, because at the time everyone believed the cosmos to be static and eternal. He called this term the cosmological constant. When Hubble showed that the universe really is expanding, Einstein reportedly abandoned the idea, calling it his greatest mistake. But now, more than 80 years later, that abandoned idea came roaring back, reinterpreted not as a mathematical patch, but as a real physical property of empty space itself. The cosmological constant provided a natural explanation for the accelerating expansion. In this picture, the vacuum of space is not truly empty. It contains a constant density of energy, and as the universe expands and the average density of ordinary matter thins out, this energy of empty space becomes increasingly dominant. Eventually, it overwhelms the pull of gravity, and the expansion speeds up. This mysterious energy of empty space came to be called dark energy, and it is, by current measurements, the dominant component of everything that exists. Roughly 68% of the total content of the universe is dark energy. About 27% is dark matter, and only about 5% is the ordinary matter we can see and touch, the atoms that make up stars, planets, oceans, and our own bodies. Pause on that for a moment. 95% of the universe is made of things we do not understand. The discovery also raised unsettling questions about the ultimate fate of everything. Before 1998, there were two main possibilities. Either the universe would expand forever, growing colder and emptier until all the stars burned out and everything faded into a thin, frigid darkness. Or gravity would eventually halt the expansion and reverse it, pulling everything back together in a great collapse. The discovery of accelerating expansion ruled out the collapse, at least as long as dark energy behaves the way it appears to. The most likely fate, as things stand, is the slow fade, an endless expansion into cold and darkness, sometimes called the Big Freeze. But there is a more dramatic possibility that cannot yet be ruled out. If dark energy is not constant, if it is somehow growing stronger over time, then the acceleration could intensify to the point where it tears apart everything in the universe. First, the great clusters of galaxies would be pulled apart, then individual galaxies, then star systems, then planets, then atoms themselves. This scenario, called the Big Rip, remains speculative, but current observations cannot entirely exclude it. Whether dark energy is truly constant or slowly changing is one of the most important questions in all of science, and several major observatories and space missions are being designed specifically to answer it. The three scientists whose teams made the discovery received the Nobel Prize in Physics in 2011. In his Nobel lecture, one of them reflected on how unexpected the result had been. His team had set out to measure how quickly the expansion of the universe was decelerating, not to discover that it was accelerating. The universe had surprised them, as it has surprised astronomers at every major turning point in this long story, from the ancient Greeks who thought the heavens were made of perfect crystal to the modern scientists who assumed the expansion must be slowing down. The nature of dark energy remains one of the most profound unsolved problems in all of science. Is it truly a fixed property of empty space, something that never changes? Or is it a dynamic force that shifts and evolves over time, perhaps growing stronger, perhaps growing weaker? Could it be a clue to something even deeper, a window into the fundamental nature of space and time and gravity themselves? New observatories and space missions, some already operating and others still under construction, are designed to measure the expansion history of the universe with enough precision to begin answering these questions. The answer, whatever it turns out to be, will shape our understanding not only of the cosmos but of its ultimate destiny. And now, let us turn to yet another new way of listening to the universe, one that does not use light at all, but the very vibrations of space and time. At just before 6 o'clock in the morning Eastern Time on September the 14th, 2015, a signal arrived at a detector in Livingston, Louisiana, and 0.07 of a second later at a twin detector in Hanford, Washington. The signal lasted less than 1/5 of a second. It began as a low, slow wobble, barely distinguishable from the background noise, then swept upward in pitch and strength, like a bird call played at an impossibly low tone, before cutting off abruptly. The waveform matched, with extraordinary precision, the predictions that Einstein's theory of gravity had made nearly a century earlier for the ripples in space and time, produced by two black holes spiraling together and merging into one. The two black holes had masses of roughly 29 and 36 times the mass of our Sun. In the final fraction of a second before they collided, they released energy equivalent to about 3 times the mass of the Sun, entirely in the form of ripples in the fabric of space itself. The peak power of that event was estimated at roughly 50 times the combined brightness of every star in the observable universe. And it had happened 1.3 billion years ago, its faint echo traveling through space ever since, weakening with distance until it nudged the mirrors of the detector by a distance smaller than the width of the core of a single atom. Einstein had predicted the existence of these ripples called gravitational waves back in 1916, shortly after completing his theory of gravity. The theory described gravity not as an invisible force, but as the curving of space and time by mass and energy. When massive objects move, especially when they accelerate violently, they produce ripples in that curvature that spread outward at the speed of light, stretching and squeezing space as they pass. But Einstein himself doubted that anyone would ever detect them. They were fantastically weak. Even the most violent events in the cosmos produced waves so feeble that they changed distances by amounts far smaller than the size of an atom. The first indirect evidence came in 1974, when two astronomers discovered a pair of neutron stars orbiting each other, one of them a type of rapidly spinning star whose regular radio pulses served as an astonishingly precise clock. By timing these pulses over many years, they showed that the orbit of the two stars was slowly shrinking, the stars spiraling closer together at exactly the rate predicted by Einstein's equations for a system losing energy through gravitational wave emission. The match between observation and theory was perfect. It was proof that gravitational waves existed, though it was indirect, like seeing the tracks of an animal in the mud rather than the animal itself. Direct detection required a completely different approach. Each detector consists of 2 arms arranged in the shape of the letter L, each arm 4 kilometers long. A laser beam is split and sent down both arms, bouncing off mirrors at the far ends and recombining at the corner. When a gravitational wave passes through, it stretches one arm and squeezes the other by an almost inconceivably tiny amount, and this change shows up in the laser light. The sensitivity required is staggering. The detector must measure a change in the length of its 4-kilometer arms that is less than 1/10,000th the width of a single proton. Achieving this took decades of engineering, the development of the most stable lasers in the world, the isolation of the mirrors from the vibrations of the Earth to an extraordinary degree, and the creation of one of the purest vacuums on the planet inside the long beam tubes. The project went through years of construction, testing, and upgrades. The initial version, which operated for several years, detected nothing, but it proved that the technology worked. A major upgrade, completed in 2015, improved the sensitivity by a factor of about 10, which meant it could survey a volume of space roughly 1,000 times larger. The very first observing run of this upgraded detector began on September the 12th, 2015. 2 days later, the signal arrived. The detection was announced publicly in February of 2016, and it sent a wave of excitement through the scientific world. For the first time, humans had heard the vibrations of space and time itself, produced by a cataclysm more powerful than anything else in the universe. 3 of the key scientists behind the project received the Nobel Prize in Physics in 2017. But the most spectacular demonstration of what this new way of seeing could do came about a year and a half later. In August of 2017, the detectors recorded the gravitational waves from 2 neutron stars spiraling together and colliding. Unlike black hole mergers, which produce gravitational waves but no light, neutron star collisions produce both. Within seconds of the gravitational wave signal, a gamma-ray satellite detected a burst of high-energy light from the same part of the sky. Over the following hours and days, more than 70 observatories on every continent and in space pointed their instruments at the source, observing it across the entire range of light, from radio waves to gamma rays. The collision was found in a galaxy about 140 million light-years away. What they saw was remarkable. The merger produced a rapidly fading fireball powered by the creation of heavy elements in the moment of collision. Careful study of the light confirmed the presence of newly created elements, and theoretical analysis indicated that the merger had produced large quantities of gold, platinum, and other heavy metals. This was the long-sought answer to a question that had puzzled scientists for decades. Where do the heaviest elements come from? The answer, it turned out, is the collision of dead stars, smashing together with such force that they forge gold from the wreckage. This event marked the beginning of a new era in astronomy, one in which the same cosmic event is observed through 2 completely different channels, gravitational waves and light, each carrying information that the other cannot provide. Future detectors, including ones planned for space and next-generation instruments on the ground, will hear mergers at far greater distances and with far greater clarity, potentially detecting gravitational echoes from the earliest moments of the universe itself. From cave painters who traced the stars on stone walls to engineers measuring vibrations smaller than an atom, the story of astronomy is a story of finding new ways to listen to the cosmos. And now, let us hear about another recent discovery, one that answered an ancient question: are there other worlds out there, orbiting other suns? On the evening of October the 6th, 1995, a Swiss astronomer named Michel Mayer stood before a room of colleagues at a conference in Florence and announced that he and his graduate student had found a planet orbiting a star beyond our solar system. The star was an ordinary one, about 50 light-years away in the constellation of Pegasus, unremarkable in every way except for what was circling it. Using a sensitive instrument mounted on a telescope in the south of France, they had detected a tiny rhythmic wobble in the star's motion, a gentle tug back and forth caused by the gravity of an unseen companion. The wobble repeated every 4¼ days, and its strength revealed a planet with a mass at least half that of Jupiter, orbiting so close to its star that its surface temperature must exceed 1,000 degrees. The audience was stunned. Nothing in the existing theories of how planets form had predicted that a giant world could exist so close to its parent star. This discovery was the first confirmed detection of a planet orbiting a normal sun-like star outside our solar system, and it changed everything. Planets, it suddenly seemed, might be far more common and far more diverse than anyone had imagined. The method used to find this first planet was elegant. When a planet orbits a star, the planet's gravity tugs the star ever so slightly back and forth. This tiny motion shifts the star's light in a measurable way, like the way the pitch of a siren changes as it moves toward you and then away from you. The effect is incredibly small. The planet Jupiter, the largest in our solar system, causes our sun to wobble at a speed of roughly 13 meters per second. The Earth causes a wobble of only about 9 centimeters per second, but with sensitive enough instruments, these shifts can be detected. Within a few years of the announcement, surveys using this technique had found dozens of planets around other stars, and the field of planet hunting had erupted from a niche curiosity into one of the most exciting areas in all of astronomy. A second method opened an even wider window. When a planet passes directly between its star and us, it blocks a tiny fraction of the star's light, producing a small, regular dip in brightness that repeats with each orbit. The amount of light blocked tells you the size of the planet, and the time between dips tells you how long the orbit takes. This transit method is ideally suited to observations from space, where the atmosphere cannot interfere, and it was this method that a remarkable space telescope was designed to exploit. Launched in 2009, the Kepler Space Telescope was given a single, dedicated task. It would stare at one patch of sky in the constellation of Cygnus, watching roughly 150,000 stars without blinking for years on end, looking for the tiny dips in brightness that would betray the presence of orbiting worlds. The data it returned transformed our understanding of the universe. By the time its primary mission ended, Kepler had confirmed over 2,600 planets and identified thousands of additional candidates. The variety was staggering. There were planets smaller than our own and planets larger than Jupiter. There were planets that orbited so close to their stars that their year lasted less than a single Earth day, and planets on orbits so wide that they took centuries to complete. There were planets orbiting two stars at once. And there were rocky planets sitting in the habitable zone of their star, the region where temperatures might allow liquid water to exist on the surface. Perhaps Kepler's most profound finding was a simple statistical one. Planets are not rare. They are everywhere. Analysis of the data suggested that, on average, every star in the Milky Way has at least one planet. Given that our galaxy contains somewhere between 200 and 400 billion stars, the number of planets in our galaxy alone is almost beyond comprehension. Among these, a meaningful fraction orbit within the habitable zones of their stars, suggesting that billions of potentially life-friendly worlds may exist in our galaxy alone. A successor satellite, launched in 2018, expanded the search to nearly the entire sky. While Kepler had looked deep but narrow, this new telescope surveyed bright, nearby stars across both halves of the sky, identifying planets close enough to be studied in detail by other instruments. It has discovered thousands of additional candidates, including worlds orbiting some of the nearest stars to our own Sun. Among the most tantalizing discoveries of this era is a system of 7 Earth-sized planets orbiting a small, cool star about 40 light-years away. All 7 planets are packed so tightly that they would fit inside the orbit of Mercury in our own solar system, and at least 3 of them sit within the range of distances where liquid water could potentially exist on their surfaces. The planets are close enough to each other that a person standing on one might see the others as large, round shapes in the sky rather than tiny points of light. This system immediately became a prime target for the most powerful space telescope ever built, which has the ability to analyze the light filtering through a planet's atmosphere as the planet crosses in front of its star. Early observations have already begun to probe the atmospheric properties of these worlds, though the question of whether any of them could support life remains beautifully, tantalizingly open. The discovery of planets beyond our solar system has transformed a question that was once purely philosophical into a science you can do with a telescope and a spectrograph. For thousands of years, thinkers had speculated about other worlds orbiting other suns, but there was no way to test the idea. Now the evidence is overwhelming. The universe is full of planets, and the search for life beyond Earth has become one of the defining scientific endeavors of our age. The 2 Swiss astronomers who made the first discovery received the Nobel Prize in Physics in 2019. The younger of them, who had been a 29-year-old doctoral student at the time, later recalled driving home in the dark through the French countryside on the night he confirmed the detection, acutely aware that the sky above him was full of worlds no one had ever seen. That awareness, once confined to the imaginations of poets and dreamers, is now grounded in hard data. The sky is full of worlds, and we are only beginning to explore them. And now, as we approach the end of our journey, let us look one last time at the sky and consider the questions that remain unanswered. the mysteries that still beckon, and the unfinished work that lies ahead. Somewhere in the high desert of northern Chile, on a mountaintop called Cerro Amazonas, construction crews are building the largest optical telescope the world has ever seen. Its primary mirror will be 39 meters across, made of nearly 800 hexagonal segments, and when it opens its eye for the first time, expected before the end of this decade, it will gather roughly 13 times more light than any telescope operating today. Not far away, on another Chilean mountaintop, a different observatory nearing completion bears the name of Vera Rubin, the astronomer who showed that the universe is full of invisible matter. This observatory will photograph the entire visible southern sky every few nights for 10 years, cataloging roughly 20 billion galaxies and watching for anything that changes, flickers, or moves. The data it produces will fill libraries, and the discoveries it makes will keep scientists busy for a generation. These are just two of the instruments being built or planned around the world and in space, and they are designed to address questions so deep and so fundamental that they touch on the very nature of reality itself. Some of these questions are ancient, stretching back to the earliest days of human curiosity. Others have emerged only in the past few decades, born from discoveries that revealed how much we still do not know. Together, they form what we might call the unfinished sky, the vast territory of mystery that lies beyond the edge of what we currently understand. The nature of dark matter is perhaps the most pressing of these mysteries. We know it is there because we can see its gravitational effects everywhere we look, in the way galaxies spin, in the way light bends around massive clusters, in the pattern of tiny temperature variations in the oldest light in the universe. But after decades of searching, no one has ever detected a particle of dark matter directly. Experiments buried deep underground, shielded from every other kind of particle, have listened patiently for years and heard nothing. The leading candidates have been narrowed but not confirmed. Dark matter makes up about 27% of everything that exists, and we do not know what it is. The new observatories being built today are designed to map its distribution across the cosmos with unprecedented detail, and perhaps, in doing so, to reveal its identity at last. Dark energy is an even deeper enigma. The discovery in 1998 that the expansion of the universe is accelerating introduced a component that makes up roughly 68% of everything in the cosmos, and yet we have no understanding of what it is. Is it a fixed property of empty space, unchanging and eternal? Or is it something that shifts and evolves over time, perhaps growing stronger, perhaps weakening? The answer matters enormously because it determines the fate of everything. If dark energy is constant, the universe will expand forever into cold, dark emptiness. If it is growing stronger, it could eventually tear the universe apart. New space missions and ground-based surveys, some already collecting data and others still being assembled, are designed to measure the expansion history of the cosmos with enough precision to begin distinguishing between these possibilities. There is also a puzzle that has emerged within the last few years and that has the scientific community quietly worried. Two different ways of measuring how fast the universe is currently expanding give two different answers, and the gap between them has not gone away as measurements have improved. One method uses the oldest light in the universe, the cosmic microwave background, and gives a somewhat slower rate. The other uses nearby stars and exploding supernovae as distance markers and gives a faster rate. The discrepancy is too large to be written off as simple measurement error, and some scientists suspect it may be a sign of something genuinely new, perhaps a kind of energy or particle that existed in the early universe, and that our current theories do not account for. Resolving this tension is one of the most urgent tasks in modern astronomy. And then there is the oldest question of all, the one that has haunted us since the first people looked up at the stars and wondered, are we alone? The search for life beyond Earth has grown from philosophy into a real working science. For decades, radio telescopes have been listening for artificial signals from other civilizations, so far without success. but with instruments that grow more powerful and more comprehensive every year. Meanwhile, a different approach has become possible with the discovery of thousands of planets around other stars. Space telescopes can now analyze the thin layer of atmosphere that surrounds a distant planet as it passes in front of its star, searching for the chemical signatures of gases that might indicate the presence of life. If a planet's atmosphere contained certain combinations of gases that should not exist together without something living to produce them, it would be a powerful clue. The most powerful space telescope ever built has already begun this kind of analysis on nearby planetary systems, and while definitive answers have not yet come, the tools to find them are now in our hands. Even the story of how galaxies form and change over time is not yet complete. The newest space telescope has detected galaxies from the very earliest period of cosmic history that are larger and more developed than our theories predicted. These impossibly early galaxies suggest that something about our understanding of the young universe is missing, though what that something is remains unclear. Every new observation sharpens the question. The nature of black holes presents its own mysteries. A worldwide network of radio telescopes working together as a single instrument produced the first image of a black hole's shadow in 2019, the dark heart of a galaxy 55 million light-years away. A second image of the black hole at the center of our own Milky Way followed a few years later. These images confirmed the existence of boundaries beyond which nothing, not even light, can escape. But they also raised questions about how these objects grow to such enormous sizes, and about what happens to the information carried by everything that falls across that boundary. A question that sits at the border between two of the greatest theories in physics, which have never been fully reconciled with each other. That reconciliation, a theory that unites our understanding of gravity with our understanding of the smallest particles, may be the deepest open question in all of physics. And astronomy may well be the arena in which it is resolved, because the universe provides laboratories, black holes, neutron stars, the echo of the Big Bang itself, where the two theories collide and where the clues to a deeper truth may be waiting. And so we come to the end of our journey, though the story itself has no ending. We began in a cave in southern France, where someone painted the stars on a stone wall 17,000 years ago. We traveled to the river valleys of Mesopotamia and Egypt, where priests and scribes tracked the movements of the sky with patient devotion. We followed the story to Greece, where philosophers asked why the heavens move as they do. We watched Copernicus quietly place the sun at the center, saw Kepler trace the ellipse, heard Galileo's telescope crack open the sky. We stood with Newton as he unified the falling apple and the orbiting moon under a single law. We watched the universe expand under Hubble's gaze, heard the echo of the Big Bang in a hiss of radio static, and felt the vibrations of colliding black holes ripple through the fabric of space itself. At every stage, the universe has turned out to be larger, stranger, and more beautiful than the previous generation imagined. And at every stage, new questions have appeared to replace the old ones, deeper and more wondrous. The sky is not finished. It never will be. And that is perhaps the most extraordinary discovery of all, that the more we learn, the more there is to learn, and that the universe, in its quiet, patient way, always has another surprise waiting. If you are still listening, I hope this story has been a gentle companion on your way to sleep. The stars are still out there, turning slowly overhead. The same stars that the cave painters watched, the same stars that the Babylonian scribes recorded on their clay tablets, the same stars that Galileo saw through his simple tube of glass. They will be there tomorrow and the night after that, patient and constant, waiting for the next person to look up and wonder. Good night and rest well.